Hello my dear students, welcome to Deeksha Karnataka YouTube channel. Your pre-boards are near and so am I here with all the important 2, 3 and 5 marker questions that is going to come in your pre-board, right? So if you watch this video along with the MCQ videos, then definitely you should secure at least 60 plus marks in your pre-board, and this video includes not only all 2, 3, 5 marker questions, also include numericals in the same lecture, okay? So if you watch this one video will solve all your doubts, all your questions, that what type of questions are going to come. Sir, will I be able to get 60 plus marks if I watch your video? Definitely yes, you have to watch this video completely till the end so that you can score 60 plus, okay? So all the questions that you mostly ask, sir, is it sufficient? Yes, it is sufficient. So but you have to watch the entire video. You should not make a suggestive cut, okay, this chapter I have not studied, I should not study it, okay? You cannot do that. And if you are starting now, this one video should be sufficient along with the MCQ video, as I mentioned. So these two videos are sufficient for your pre-board 60 plus. We will be doing more and more videos for your pre-board, so don't worry, I will be there in live as well to help you out with your doubts. So first, as I mentioned, this is a complete pre-board package, so all the chapters are included in this single video, okay? So I have not separated the video based on the chapters. I am giving you all the questions, important questions from this for your pre-board, okay? So let us start. So question number 1, state Coulomb's law in electrostatics and explain it in the case of free space. So this question might come like state and explain Coulomb's law, or write Coulomb's law in vector form. So all types of varieties of Coulomb's law might come. I will tell you how to answer that as well. So first of all, you have to write the statement, okay? Coulomb's law states that electrostatic force between 2 point charges is directly proportional to product of magnitude of the two charges and inversely proportional to the square of the distance between them. And mathematically it can be written as, so try to practice the vector from here onwards, so that if the question comes that what is the vector form of Coulomb's law, you know what you have to do. Okay, F vector equals to 1 by 4 pi epsilon naught q1 q2 by r square r cap. Now if the question comes right in vector forms, the diagram is necessary. So what is the diagram? Nothing special, only thing you have to show that this is q1, this is q2, okay, this is your force and this is r cap, okay, this is your force and this is your r cap, okay? So this is the simple diagram. If you draw it, that's sufficient. There is one more diagram in your NCERT textbook. If you want to draw that, then this expression slightly varies, so that is also okay. Okay, if you draw that, the expression you have to change accordingly, but this is the simplest diagram. Force you have measured, r cap vector you have shown, so no problem in that case, okay? And also you have to mention what are all the charges, q1 and q2 point charges, epsilon naught permittivity of free space, r is the distance between q1 and q2, r cap is the unit vector. Now let's move on to the next question. Now this question can come, all the questions that we are going to discuss in 2 marker, 3 marker segment can come as a 2 marker question, can be asked as a 3 marker question as well. So be prepared. So if I am giving you 3 options, 3 points, then you have to remember all the 3 points, because you don't know what marks that question might come, okay? So 2, 3 marker questions are generally common. Sometimes it can be asked as a 2 marker, sometimes it can be asked as a 3 marker as well. Derive the expression of torque on an electric dipole placed in an uniform electric field. So here we have electric field and we also have an electric dipole, okay? So this is positive charge plus q, this is negative charge minus q, okay? So what is the torque acting on it? We have to calculate the torque acting on this charge. So how to do that? So when there is an electric field present, okay, the positive charge experiences a force in the direction of the electric field. So this will be the direction of the force acting on the positive charge. What about the negative charge? Negative charge experiences a force in the opposite direction of the electric field. So the negative charge will experience a force in the opposite direction. Okay, now what is the magnitude of these two forces? The magnitude of these two forces will be same, that is given by, so magnitude wise direction will be different obviously, but magnitude wise it will be same, Q into E. This is plus Q into E, this is minus Q into E, but because magnitude is more important, that's why we will say that, okay, magnitude wise both forces are same. Now what is torque? So if you have to go back to your PU1 concept little bit. So in PU1 you have learned that torque is when two equal and opposite forces acting on a body. Okay, the torque is given by magnitude of any one of the forces, times the distance between the forces. The distance is what is the distance over here? Distance is nothing but this distance. Okay, so this is the distance, say L. So F into L will be the torque. Very simple. Torque is force, magnitude of force into the distance between the forces. Remember, two equal and opposite forces must be acting on the object. Now here object is obviously the dipole. Now how to calculate L, that is the main thing. Okay, so if this angle say theta, then this angle will also be theta. Okay, parallel lines, a constant electric field, uniform electric field, so the angle theta will remain constant. Now we know that the positive and negative charges are separated by a distance given by 2a. Okay, positive and negative charges are separated by a distance called 2a. So this is basically a triangle. This is basically a triangle, and if you can find the distance between the charges, so this is 2a, this is L, this is theta. So and this angle is 90 degrees obviously. Perpendicular distance between the forces means perpendicular distance. Now what is L in terms of 2a? If we can figure that out, then we will be able to solve it. So this is the hypotenuse, and with respect to this angle, this is perpendicular. Okay, so perpendicular by hypotenuse is sine theta. So sine theta equals to L divided by 2a. So what is L? L is 2a sine theta. Right, so we have figured this out. Now just only thing we have to put is the value of the force, that is Q into E, and value of L, which is 2a sine theta. Right, now reorganize them slightly. So 2aq into E sine theta. Right, now what? So now we know that 2a into Q is something which is a constant for a given dipole, which is the dipole moment. So this will be substituted by dipole moment P, and we will write Pe sine theta, where we have to mention P equals to 2qa equals to dipole moment. Make sure you write them properly. Now what is a torque? Torque is a vector quantity, right? So you cannot leave it in a scalar form. So in vector form, torque is given by P cross E. Okay, what happened to the sine theta? What happened to the sine theta? So when we do the cross product, sine theta is a byproduct of cross product, right? So if you remove the cross sign, okay, and if you express the same quantity in scalar form, then sine theta comes automatically, right? So this is the simplest derivation of this. Okay, remember, mention this. All portions that I have drawn and written in the board are important. You have to do everything. I have not written anything extra except this triangle picture. Okay, this triangle picture is just for your understanding, so you don't need to draw that triangle. Now next question, write any three properties of electric charges. So as I mentioned, this question can be asked as a 2-mark question, can be asked as a 3-mark question. Additivity of charges. Charges are additive in nature, that means you can simply add the charges algebraically. Okay, quantization of charges, all charges are integral multiple or integer multiple of smallest charge, small e. Conservation of charges, total charge in an isolated system is conserved. So you have to mention the properties and properly explain it using one line at least. Okay, charges are additive in nature, you can mention, or charges are scalar. or charges can be added like a scalar. Okay, whatever you are comfortable, you can write that over here. But for quantization of charges and conservation of charges, you have to mention, if you just mention additivity of charges, quantization of charges, conservation of charges, I have seen that many students do that. If teacher is slightly strict, they will deduct marks. Okay, quantization of charge does not make any sense unless you explain it that all charges are multiple of smallest charge, small e. Okay. Now, before I continue, I just wanted to tell you that all of you are preparing for your pre-boards as well as your KCET exam, right? In future, KCET exam is there. So, ABHYAS KCET test series 2026 is live. So, it is available for only a price of 1499, and what you will get 35 KCET test papers. You will also get chapter-wise KCET PYQs last 10 years. Right now, PU2 chapters are there. PU1 chapters will be added on later on. Real-time KCET exam pattern and timing. So when you are attempting a test, you have to attempt the test in 60 minutes so that you are habituated with the time management. Okay, time management is essential and most important for KCET preparation. So ABHYAS KCET test series not only brings you a KCET level questions but also gives you a chance to practice them within the given time. PCMB, all subjects are covered. Physics, chemistry, maths and biology, all 4 subjects are covered. Also remember that you can attempt the test series in multiple times, does not restrict you. So even if you have completed it once, you can attempt it again. Okay, and obviously it is trusted by the toppers. You can see all the toppers last year from 2025 batch, they all have opted for ABHYAS and they did excellent in the KCET exam. Okay, only few of them are listed over here. We have a long list of toppers from our ABHYAS KCET test series only. Okay, so now and the price of the product is 1499, very much affordable. I hope you have already purchased it. If you have not purchased it, go and purchase it today so that you can enjoy and prepare for your KCET exam with confidence. Okay, now let's continue with our discussion. Write 3 properties of electric field lines. Again, 2 properties, 3 properties, all can come. Electric field lines may start from positive charge and end at negative charge. So positive charge, it starts with positive charge, it can end at negative charge, or it can start at infinity and come back to a negative charge, and it can start at positive charge, go towards infinity based on the charge. 2 electric field lines never intersect each other. The easiest property to remember. Electrostatic field lines do not form any closed loop. So this is the difference between electric field lines and magnetic field lines. Okay, electric field lines do not form closed loops. Magnetic field lines, they do form closed loops. Okay, so this is the difference between electric and magnetic. So if you study electric with the difference of magnetic, so you don't need to study magnetic field separately. Okay, just you change the positive and negative are obviously different, but if you remember, magnetic field lines also do not intersect. Next question, what is an equipotential surface? What will be the shape of equipotential surface corresponding to a single point charge? Let's see. Any surface which has same electric potential at every point is called an equipotential surface. The shape of equipotential surface is spherical for a single point charge. If they ask you to draw it, you have to take a point charge and you have to draw some concentric circles. That's it. Take your compass and draw concentric circles. Don't draw like me. Okay, try to draw it properly so that you get marks. Now next, write 2 properties of equipotential surface. It can be 2 properties, it can be 3 properties as I mentioned. Okay, 2 or 3, both are possible. No work is done in moving a test charge over a equipotential surface. Okay, so when you are moving a test charge from one point to another in an equipotential surface, work done is 0. Based on this concept also, we might get a MCQ question. Electric field is always normal to the equipotential surface at every point. Okay, electric field is always normal to the equipotential surface at every point. No 2 equipotential surfaces can intersect each other. Same as electric field lines, magnetic field lines, equipotential surfaces can also not intersect each other. Now next, On what factor does the capacitance of a parallel plate capacitor depends? Okay, so first you have to start with the expression for capacity, that is C equals to A epsilon naught by D. Okay, you can mention that what is A, what is D, but not necessary, but you have to write the so capacitance is directly proportional to area. Now here you can write area is given by A. Inversely proportional to the distance between the plates, that is, it is proportional to 1 by D. Okay, it is proportional to A, it is proportional to 1 by D. Try to write it in words, do not just write in symbols. If you are writing in symbols, you have to explain the symbols. If you just write proportional to A symbol, then you have to explain A refers to area. If you just write proportional to 1 by D, then you have to mention D represents distance between the plates. So that you have to be careful. I have seen students, they write 1 proportional to A, do proportional to 1 by D. Don't do that. You have to mention what is A, what is D, otherwise marks will be deducted. Directly proportional to the dielectric constant kept between the medium, so it is directly proportional to, so if you are writing that, you have to use the K symbol over here. K is the dielectric constant. Okay, so it is proportional to dielectric constant K. Dielectric constant is not epsilon naught, it's a constant. Epsilon naught is the free space permittivity, which is a constant. K is dielectric constant. So if you have a capacitor with some dielectric constant between the plates, that is basically the dielectric medium. Clear? Now let us continue. Obtain the expression for effective capacitance of two capacitors connected in parallel. So we have two capacitors connected in parallel. Now remember, be it resistance, be it capacitance, when they ask you about parallel combination, parallel refers to same voltage, series refers to same current or same charge. Okay, so in parallel combination, both capacitors have same voltage. So suppose this is C1, this is C2, and this is V. They are connected in parallel combination. Parallel means one after another. Okay, now what they have asked you, obtain the expression for effective capacitance of two capacitors. So effective capacitance means you have to replace these two capacitors using a single capacitor so that everything remains same. Everything remains same. Only the capacitor is now only one. Okay, so if you have a chance, if you want to replace these two capacitors with a single capacitor, then this is called equivalent capacitance. Now what is the meaning of that? So whatever total charge that was flowing, okay, that same total charge will be flowing for this capacitor as well. So suppose the charge that is stored over here is Q1, stored over here is Q2, and obviously from the conservation of charges we can say that the total charge Q is equal to Q1 plus Q2, and that same thing should be followed for this capacitor as well. Okay, now let's see. So what is the voltage drop across this capacitor? First capacitor, voltage drop across C1. Okay, voltage drop across C1, V equals to Q1 C1, and voltage drop across C2, V equals to Q2 C2. Sir, you have made a mistake. You have written both of them as V. How is it so? So that is the main part of this derivation. In parallel combination, voltage remains constant. So in parallel combination, voltage remains same. Okay, so that is the major point that you have to remember. Okay, so from here we can write that Q1 equals to V by C1, and from here we can write Q2 equals to V by C2, right? Extremely sorry, I made a small mistake. Yes, I know many of you are commenting, sir, you have done mistake. Don't worry, it was a purposeful to check if you have understood or not. So it will be Q1 equals to C1V and Q2 equals to C2V. Yes, again voltage is same, that's why both of them are same voltage V. So what is the total charge? Total charge is Q1 plus Q2, so it will be C1 plus C2 into V. This is for individual case. What about the equivalent case? For equivalent circuit, Q equals to C equivalent into V. It will also have the same voltage. It will also have the same voltage, right? So if you compare these two Q, so equation number 1 and equation number 2, if you compare these two, you will see that C equivalent into V equals to C1 plus C2 into V. So from here we can say that C equivalent is equals to C1 plus C2. Very simple, easy derivation. Okay, but out of parallel and series, one derivation is very important. One of them must come in your pre-board. Okay. Obtain the expression for effective capacitance of two capacitors connected in series. Now we will do the series one. In series one we have two capacitors C1 and C2. Everything is same. Circuit diagram is almost same. C1, C2. Only thing is in series combination the charge remains same. In series combination total charge is same for all capacitors. Maybe 2, maybe 3, okay, does not matter. Okay, total charge remains same. Now what is the equivalent circuit? Equivalent circuit is same. Whatever was the equivalent circuit in the parallel, same equivalent circuit will be there for series as well. Okay, so this is V, right? So now what? Again the voltage in this case will be different. Suppose the voltage drop across capacitor 1 is V1, voltage drop across capacitor 2 is V2, and voltage drop across C equivalent is V. Okay, so what is V? So V is V1 plus V2, right? So total voltage V should be equals to voltage drop across capacitor C1 plus across capacitor C2, because there are no other capacitor present. So voltage drop should be same for both capacitors. Now for capacitor C1, okay, Q equals to C1 into V1, or V1 equals to Q1 by C1. For capacitor C2, Q equals to C2 V2, or V2 equals to Q by C2. Okay, now here charges are same, that's why I am using the same charge. Right, charge are same, both charges are Q, but what is changing is voltage. Voltage is different. So previous case charge was different, voltage was same. In this case charge are same, but voltage is different, right? Now what about the equivalent capacitance? For equivalent circuit, okay, this is a shortcut of writing equivalent EQ. CKT is for circuit. Okay, so for equivalent circuit we can write that Q equals to C equivalent into V, or V equals to Q upon C equivalent. Now we will use this formula, right? We know that V equals to V1 plus V2. Now combining the equation 1, 2 and 3, this is 1, this is 2 and this is 3. What we can say, on our left hand side we have V, so Q by C equivalent equals to Q by C1 plus Q by C2, or 1 by C equivalent equals to 1 by C1 plus 1 by C2. Okay, this is the answer. But if you are solving some numericals based on this concept, this equation can be slightly modified into C1 C2 by C1 plus C2, right? You just need to add them normal like variables and then take reciprocals on both sides, because see here we have 1 by C equivalent. So this is a shortcut formula. You can show that in this derivation as well, no harm, but if you don't want to show it, you can skip it, because only because two capacitors are asked you can show this, otherwise it is not required. Now let's move on. Derive the relation between electric field and electric potential due to a point charge. This is a very important question. Okay, this is a very important question. Now let's see. First you have to start with the diagram. Okay, the diagram is important here. Surface A and surface B represents two equipotentials. They represents two equipotentials. The voltage of voltage of A is V, voltage of B is V minus delta V. Okay, and the distance between these two equipotential is delta L, and electric field is pointing upward. Electric field is pointing upward, right? Now if you have a charge, say small charge Q, you have a small test charge Q, and you want to move it from this point to this point. Okay, so what is the work done that you have to do? What is the work done that you have to do? The work done is basically difference in potential, right? Work done per unit charge is difference in potential. So first of all, work done. So work done to move this charge, we will use this symbol. Okay, work done to move this charge small q from A to B is given by force acting on it into the displacement. Okay, dl. Let me not write delta L, change the symbols so don't get any confusion. Okay, so this will be dl and this will be dv. Okay, so small work done is given by force into dl. Now what is force? Force acting on a charge, is given by Q into E. Okay, and the distance is very small, so we can assume electric field is constant. Okay, we can assume electric field is constant in this small range. So force is given by Q into E. So that means if we put it over here, we will get Q into E into dl. Okay, so Q into E into dl is the small work done to move this charge from here to here. So what is the change in potential? Change in potential or potential, we know that this small work done divided by charge. Okay, small work done divided by charge will be given by the change in potential. What is change in potential? Initial final potential is V minus dV, and initial potential is V. Now why this is minus? Because electric field always points from higher potential to lower potential. The direction of electric field is always from higher potential to lower potential. That's why there is a minus over here. So it will be minus dV. So minus dV is the potential difference. So dW by Q is potential difference. Now put the value of dW, Q into E into dl by Q equals to minus dV. Q cancels, so we get E into dl equals to minus dV, or E equals to minus dV by dl. Okay, diagram is compulsory in this particular case, and this is the easiest derivation of this particular question. Okay, the derivation that I have used, if you remember the symbol in textbook, in other books they have used complicated symbology, and you might get confused, but if you do the derivation like this, it is no chance of any mistakes. Okay, remember final minus initial is always the potential difference, and that is the work done per unit charge. So if you take only unit charge at the beginning, that is also fine, but as I mentioned, this is the easiest way to remember. Practice it 2-3 times and it will be always with you till your board exams. Okay, this is a very important question, not only for pre-board but also for your final board exam. Next question, Write the expression for drift velocity in terms of current. Explain the terms used. So obviously current is given by NEAVD. I always ask my students to remember this equation. This is a very important equation. So I equals to NEAVD, and from here you can say VD equals to I by NEA. Okay, where Vd is drift velocity, I is the current in the conductor, number density of the conductor is given by small n, E is charge of an electron, and A is the area of cross section of the conductor. Okay, sometimes this question might also be asked as what is the relationship between Vd and current density. Current density is given by 1 by Ne into J. Okay, J is I by A is J, I by A is J. Okay, you can write in scalar form, or if you are writing vector form, Vd and J vector should be there, otherwise this is fine. Okay, now let's move on. Define drift velocity and mobility of free electrons in conductors, or define mobility, mention its SI unit. Both type of questions can come. Let's see. Drift velocity is the average velocity with which the free electrons drift under the influence of an electric field called drift velocity. Okay, so drift velocity is only when then an external electric field is applied. Okay, so electron starts to drift under the influence of an external electric field, and that velocity gained by electron due to the external electric field is called drift velocity. Okay, so drifting is due to like a swimming. Okay, when there is a electric field, some water is flowing and you are just trying to move with the water, that is called drifting. Okay, mobility is the mobility of free electron is defined as the drift velocity of electron per unit electric field. Okay, so mobility or mu is drift velocity per electric field. Okay, so this is the mobility, how quickly electron can move from one place to another when electric field is applied. The SI unit of mobility is meter square per second per volt, or meter per second per Newton into Coulomb. Okay, so you can remember any one of the unit, but it is very essential that you remember one of them. Okay, because the unit of mobility is very common question that might come in your pre-board. Mention two limitations of Ohm's law. Okay, Ohm's law is applicable only if all the physical conditions remain same. That means if the conductor starts to melt, then Ohm's law will not be applicable. Okay, so all physical conditions should remain constant. Ohm's law is not applicable at very low and at very high temperature. Okay, at very low and very high temperature, Ohm's law cannot be applied. Ohm's law is not applicable for non-ohmic devices like semiconductor devices, discharge tube, etc. In these cases, Ohm's law cannot be applied. Let's move on. Name the two factors on which the resistivity of a wire depends. Okay, so first of all, resistivity is not same as resistance. Okay, resistance is given by R is equal to rho L by A. So if the same question is asked about resistance, you should mention length directly proportional to length, inversely proportional to area. But this resistivity is a constant. Okay, resistivity is given by the symbol rho. It is not resistance. Okay, so be careful. If the question comes over two factors on which resistance depends, then it will be length and area. If it is resistivity, then it will be material as well as temperature. So be careful what is asked. Resistivity is not same as resistance. Okay, students study resistance, and in the exam they ask about resistivity, and they write what is they studied about resistance, and they write it. Similarly, if it is asked about resistance also, students remember resistivity and they start writing about resistivity. So be careful. Resistivity and resistance are two different questions, and both of them might come. Okay, one of them might come from you, another one might come for another student. Okay, so all possibilities are there, resistance and resistivity. Remember, material of the wire and temperature of the wire are two important factors on which resistivity depends. Resistance depends on length and area. Okay, when does a current carrying conductor placed in an uniform magnetic field experience maximum force, minimum force? First of all, what is the force on a current carrying conductor in a magnetic field? The force acting on a current carrying conductor is given by not QVV. QVV is force on a charge. It will be BIL sin theta. Okay, so this is the force acting on a current carrying conductor. When this will be maximum? When sin theta is maximum, that is theta equals to 90 degree. When the angle between current and magnetic field is 90 degrees, the force is maximum. Okay, same thing you have to write. When the force between current and angle is theta equals to 0 degree, force is minimum. Okay, so write it in complete sentence. Okay, when the angle between current and, or you have to write this expression and write when theta is equal to 90 degrees, force is maximum. When theta equals to 0 degrees, force is minimum. Okay, next, when the current is flowing in the, okay, so this is already written. When the current is flowing in the perpendicular to the direction of magnetic field, force is maximum, so that is theta equals to 90 degrees. And when the current is flowing in the same direction as magnetic field, theta equals to 0 degrees. Okay, and force is given by BIL sin theta. Okay. Next question. Derive an expression for angular frequency of revolution for a charged particle moving perpendicular to the uniform magnetic field. Obtain an expression for the radius of circular path taken by a charged particle moving perpendicular to the uniform magnetic field. This is also a very common question in pre-board level. So here we have a magnetic field and a charge is rotating in a circular path, right? We know that if velocity vector and the magnetic field are perpendicular, then it rotates in a circular path. Okay. Now, what is the expression for this radius? We have to do two things. First of all, we have to find the radius and angular velocity omega. These two things we have to calculate. Now, how can we calculate two things? Derivations is same, last step is slightly different. So, first of all, whenever there is a circular motion, okay, there is a force that acts on the system. Okay, what is that force? That force is called centripetal force. No matter what type of circular motion, if there is a circular motion, centripetal force has to be there. And centripetal force is not a natural force. It has to be provided by some other natural forces. For example, Earth is rotating around the Sun, okay, in a circular or almost circular orbit, slightly elliptical. There is a centripetal force that is acting on Earth. Now, who is providing the centripetal force? Centripetal force is provided by the gravitational force of between Earth and Sun. Okay, so if Sun disappears, then Earth will no longer be able to continue its circular motion because the gravitation will be gone, right? Similarly, the charge is rotating in a circular path, means someone has to provide the required centripetal force, otherwise this circular motion would not be possible. So who is providing the required centripetal force? Okay, so whenever you see a circular motion, always ask who is providing the centripetal force. So centripetal force in this case is provided by the Lorentz force, that is Q into V into B. Okay, right? QVV is the centripetal force. QVV sin theta. In this case, theta is 90 degrees. Okay, the angle between velocity vector and the magnetic field vector is 90 degrees. So sin theta is 1. Okay, so centripetal force is Q into V into B. Now centripetal force itself has its own expression. What is that? That is mv square upon R equals to Q into V into B. Okay, so this is the expression for centripetal force, and centripetal force is provided by Lorentz force. So from there we can write this. Now you can easily calculate the radius from this expression. So radius is given by mv by qb. Okay, very easy derivation. Diagram is important, and you have to write the centripetal force is equal to the Lorentz force. Lorentz force is providing the required centripetal force for the motion, and then you can write this. Okay, so just simple derivation, and it is a 3 marks generally comes, so 3 marks will be guaranteed. So this is done. Now, as I mentioned, you also sometimes may be asked to find the angular frequency. This is normal radius. So radius part, this is the second part. Okay, this is the second part. This is the second part derivation. What about the first part derivation? So this is the first part. First part question can be easily derived. Again, we will start from the same expression, and we will write mv by r equals to qb. And what is v? In terms of rotational motion, V can be, this is part 1 derivation, V can be written as, so from here directly part 2, and from here we are going into part 1. V in rotational motion is written by R into omega. Okay, so M into R into omega divided by R equals to QB. Okay, you have to write V equals to R omega. Omega is angular frequency. Okay, so R cancels, and you get omega equals to QB upon M. So as you can see, radius depends on velocity V, but omega is independent of velocity V. Okay, omega only depends on mass of the charge, amount of charge, as well as magnetic field. Okay, whereas radius depends on mass, charge, magnetic field, as well as velocity. Angular velocity or angular frequency is independent of linear velocity. Very interesting, right? Let's move on. What is Lorentz force? Write its expression and explain the terms. The force acting on a moving charge particle in presence of electric and magnetic field is called Lorentz force. Very important question. Lorentz force is given by Q into E plus Q into V cross B. So this is the electric force component, and this is the magnetic force component. So when both electric and magnetic field is present and a charged particle is moving inside this both electric and magnetic field, the total force, the combined force experienced by the charged particle is basically called the Lorentz force. Now here Q is called, Q is obviously the charge, E is electric field, V is velocity of the particle, and B is the magnetic field. How can a galvanometer be converted into a voltmeter? Explain with diagram. This is also very important question. Okay, galvanometer to voltmeter, galvanometer to ammeter, both are important. A voltmeter should have a very high resistance, as it is connected to a parallel in the circuit. Okay, parallel means suppose you are connecting resistance in parallel. If the resistance of the parallel connection is itself is low, then most of the current will pass through the galvanometer itself. Okay, and there will be very less current passing through the actual resistor. So when you put the galvanometer, you will get a wrong reading, because in the absence of galvanometer, there will be a very high current that will pass through the resistor, but as soon as you connect the galvanometer, most current is drawn by the galvanometer itself. The measuring device should not change the original circuit conditions. Okay, so to do that, measuring devices should be neutral. Okay, so to do that, what it has to have? It has to have a very high resistance. Galvanometer should have to have a very high resistance. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with it. This way, the overall resistance of the galvanometer will be very high, and a very small amount of current will be drawn by the galvanometer. Okay, and the diagram is given by this. Diagram of the galvanometer to voltmeter is given by this. The current, the maximum current that should be passing through the galvanometer is given by Ig, okay, and Ig, if the maximum current passes through the galvanometer, then that is also the max deflection of the galvanometer, okay. Sometimes problems might come, so you have to remember that the voltage drop across the galvanometer is given by Rg plus R into Ig, okay. So that is the voltage drop across the galvanometer, okay. We generally do not use Rg, what we use is G. So voltage drop across the galvanometer is G plus R into Ig, okay. So this is the formula for solving problems, you might remember, okay. Next question, how can a galvanometer be converted into an ammeter? Explain with diagram. As I mentioned, both galvanometer and ammeter are important. An ammeter should have a very low resistance as it is connected in series with the circuit, okay. So again, ammeter, if they have a very high resistance, it will change the overall resistance of the circuit. So the current that you are supposed to get, you are getting a different current. That is not our desire. What we are expecting is that ammeter should also not change the circuit condition. So if you are connecting something in series, that original resistance should be very low so that it does not affect the working of the circuit, right. In parallel means ideally it should have infinite resistance, and for an ideal ammeter the resistance should be 0. Ideal ammeter should have a 0 resistance, ideal voltmeter should have a infinite resistance. An ammeter should have a very low resistance as it is connected in series in the circuit. This is achieved by connecting a suitable low resistance S in parallel called shunt, okay. The name is given shunt, with a galvanometer. This way the overall resistance of the ammeter remains low and the galvanometer is converted into an ammeter. The circuit diagram is given by this, okay. So here you can see the galvanometer with its own resistance. Rg is the resistance of the galvanometer. Generally we denote it by G, okay. G for genius, okay. Some textbook denoted by Rg, okay. So G is the resistance of the galvanometer and Rs is the shunt resistance. Now when it is converted into galvanometer to ammeter, what happens is that the total current that is passing through is I. The current, the current that we are measuring. This current we are trying to measure, but galvanometer cannot afford this high current to pass through it. So it will only have a small current Ig, that is the maximum current can be allowed to pass through the galvanometer, okay. And what happened to the remaining current? The remaining current will quietly pass through the shunt. The remaining current will quietly pass through the shunt. And what is the combination here? Galvanometer and the shunt, they are connected in parallel. And what we know about parallel combination? Parallel combination means the voltage drop should be same. So whatever is the voltage drop across this shunt, the same voltage drop should be across the galvanometer. So we can say that Ig into G, that is the voltage drop across the galvanometer. V is equal to IR, V equals to IR, same concept, Ohm's law. So voltage drop across the galvanometer is Ig into G, and voltage drop across this small resistance is given by Is into not Is, I minus Ig into S. S is the small resistance, okay. Now from here you can calculate the value of I, which is very, very essential. So Ig into G plus Ig into S equals to I into S, okay. So from here you can calculate the total current that you are measuring, that is I equals to G plus S by S into Ig. This is both way equation, you can calculate Ig as well as I, okay. Now remember that because we are measuring I, Ig is a known quantity. For a given galvanometer, the maximum current it can withstand is already known when it is manufactured. So Ig is a known quantity, G and S, G is also known quantity, only S you have to figure it out. So this formula you have to write when you are writing the conversation, as well as when some numerical question it might come, you have to use this formula to solve. State and explain Biot-Savart's law, write its vector form. So Biot-Savart law, whenever you are writing Biot-Savart law, the diagram is essential. Okay, you have to draw this kind of diagram where a current carrying wire is shown. Okay, you are finding the magnetic field at some distance dB. The angle between the direction of the current and this vector is theta, and this is the current element. This dl is current element. Okay, the magnitude of magnetic field at any point P due to current element dl is directly proportional to the strength of the magnetic strength of the current I, directly proportional to the length of the current dl, directly proportional to the sine of the angle between the current element and the line joining the given point and the midpoint of the current element, inversely proportional to the square of the distance between the current element and the point. So the magnetic field dB is given by 1 by mu naught mu naught by 4 pi, this is the constant, times I dl sine theta divided by r square. This is the mathematical formula of Biot-Savart's law. Okay, you can remember it. If you write the Biot-Savart's law as a statement with the diagram, you should also write the equation for it. Okay, generally it's a 3-mark question. It is not a 2-mark question, it is a 3-mark question. Write 3 differences between diamagnetic or between diamagnetic and paramagnetic, diamagnetic and ferromagnetic, paramagnetic and ferromagnetic. Okay, so this is any combination of 2 can come. Dia-ferro, dia-para, para-ferro. Okay, any one of the difference should come in your pre-board, and there is one way so that you can remember it. Okay, and also remember that if you want to download the PDF of this lecture, then don't forget to join our WhatsApp channel. The link of the WhatsApp channel is given in the description. This entire lecture will be available as a PDF in our WhatsApp channel only. The link of this PDF will be shared exclusively on our WhatsApp channel, so don't forget to join the WhatsApp channel. Okay, so remember how to write the differences. You have to write the property on which you are writing the differences. Okay, this gives the clarity to the examiner that what is the property that you are writing. Diamagnetic, paramagnetic, ferromagnetic, you remember it this way. Any two, if diamagnetic and paramagnetic is coming, you have to write this. If dia and ferro is coming, then dia and ferro. If para and ferro is coming, then para and ferro. Okay, so remember this. So magnetic behavior, diamagnetic, these are weakly repelled by magnetic field. Paramagnetic, these are weakly attracted by magnetic field. Ferromagnetic, these are strongly attracted by magnetic field. Now magnetic susceptibility, have a small negative magnetic susceptibility, chi is less than 0. Have a small positive magnetic susceptibility, chi is greater than 0. Have a large positive magnetic susceptibility, chi is very, very greater than 0. What about effect in magnetic field? So based on it is a 3-marker or 2-marker, you have to write 2 points or 3 points. If it is a 2-marker question, 2 points are sufficient. If it is a 3-marker question, you have to write 3 differences. Okay, induces magnetic moment in the opposite direction of the applied field, induces magnetic moment in the same direction of the applied magnetic field, induces a strong magnetic moment in the same direction of the magnetic field. So para and ferro are very close to each other, but they are like relatives, but they lost long before. Okay, in the childhood they got separated, and now one has become ferro, one is become para. Okay, diamagnetic is somewhat different. Okay, now let's move on to the next question. Write any 3 properties of magnetic field lines. This is also very, very important question. Magnetic field lines form continuous closed loops. The tangent to the field at a given point represents the direction of the net magnetic field at that point. Larger the number of field lines crossing per unit area, stronger is the magnetic field B. The magnetic field lines do not intersect each other. Okay, as I mentioned, magnetic field lines are continuous closed loop. Unlike electric field lines, they are not closed, they are open loops. Okay, and obviously magnetic field lines do not intersect as usual. The tangent to the field line drawn at a point represent the direction of the net magnetic field at that point. Okay, any 3 points you can remember. I have given 1 point extra in magnetic fields. Next, state and explain Gauss's law in magnetism. Okay, in electrostatics it might come as a separate question, it might come as a 1 marker or 2 marker question. We will discuss that in one of the derivation, but first state and explain Gauss's law of magnetism. Gauss's law of magnetism is the net magnetic flux through any closed surface is 0. Okay, it is easy to remember. The total magnetic flux, remember it's magnetic flux, not electric flux. The total magnetic flux through any closed surface is 0, that is B dot ds closed integral is 0. Closed integral represents closed surface. So this integral represents closed surface, and if you write a small s over here, that is sufficient. Physical significance, magnetic monopoles do not exist. Okay, so magnetic monopoles do not exist. That is the basic thing. Okay, magnet always comes as a dipole. Okay, magnets are always dipoles. Electric, in case of electricity, electric charges, dipoles are optional. It is not obviously you can separate positive and negative charges. In case of magnetism, separate north pole or separate south pole is not possible. South and north are always come in a pair. That is, magnetic field lines always form closed loop. Okay, so if you consider a surface, okay, if some lines are passing through this, the same line should also exit. Okay, so magnetic monopoles do not exist. That means whatever field lines is passing crossing the surface, it will always, entry and exit should be same. Okay, entry and exit same means net flux is 0. Okay, net flux means entry minus exit or exit minus entry, but in this case entry is equals to exit, so that means net flux is 0. State Faraday's law and Lenz's law of electromagnetic induction. So this is also very important. Mostly Lenz's law will come, but in some cases Faraday's law can also come. Faraday's law is the time rate of change of magnetic flux through a circuit induces EMF in it. So if you change the flux linked with the coil, then it will be inducing a EMF. The polarity of the induced EMF is such that it tends to produce a current which is opposes the change in the magnetic flux that produces it. Also remember that this is a consequence of conservation of energy. Lenz's law is conservation of energy. Okay, Lenz's law is direct consequence of conservation of energy. Next, mention any two factors on which the self-inductance depends. Okay, so obviously self-inductance equation, this is a new type of question, might come in your pre-board, so be prepared. The equation of self-inductance is given by L equals to mu naught n square A into L. Self-inductance is directly proportional to the square of the number of turns per unit length. Okay, so the square of the number of turns per unit length. Self-inductance is directly proportional to the cross-sectional area A of the solenoid. Okay, it is directly proportional to the cross-sectional area A of the solenoid. Self-inductance is directly proportional to the length of the coil. Okay, total length of the coil L, it is also directly proportional. Derive the expression for motional EMF induced in a straight conductor moving perpendicular in uniform magnetic field. So first of all, in this derivation also, the diagram is compulsory. You cannot derive it without the diagram, and whenever you are drawing the diagram, try to draw it using black ballpoint pen, that will be clear, or if you are using pencil, use HB pencil for clarity. And obviously do not just simply draw using hand, use your scales, use compass as and when required. Okay, do not just simply draw using hand. Okay, now let's see. So here we have a circular frame on which there is a rail. This is a square rail through which this train like structure, this is a train like rod which can move. Okay, and it is moving with the velocity v. Okay, so the explanation of the diagram is required in this case. Okay, so I am just writing it. Explain the diagram. Okay, explain the diagram, which is essential. Now what? Now you have to first of all, velocity is given. You have to calculate what is the flux linked with the coil. So flux linked is given by the magnetic field into area. Flux linked with the any coil, or in this case it is a loop. Okay, it's a closed loop. So flux linked with the loop is given by magnetic flux into area, magnetic field into area. What is area in this case? The area of this square in this rectangle is given by the length, which is given by L. If you see, the length is given by L, and the distance between these two ends, which is given by x. Okay, now x is not constant, x is changing with time, because this rod is moving. We will do that, but first find the area. Area is length into breadth, that is L into x. Okay, so this is the flux. Now if a flux linked with the coil, will there be an induced EMF? If there is just simple flux linked with the coil, no, the flux has to change with time. Okay, so the induced EMF is given by d phi by dt, and actually it is minus d phi by dt. Negative sign represents Lenz's law. Okay, Lenz's law gives you this negative sign. Okay, now we have to put this over here. So minus d dt of b into L into x. B into L into x. Now B is constant, magnetic field is not changing, so magnetic field here is constant. The length, obviously this length is constant, it is not changing. Only thing that is changing is x. What is the meaning of ddx? ddx represents rate of change of ddt represents rate of change of something with respect to time. With respect to time, only x is changing, so x is the variable, remaining terms are constant. So in case of differentiation, we can take the constant out of the differentiation, and we can write dx dt. Okay, dx dt. Now if we take this as b into L minus dx dt, now what is dx dt represents? That is the major question. So what is x? X is this distance, and rate of change of this distance is what? Rate of change of this distance basically gives you this velocity, right? Rate of change of displacement gives you velocity, and here minus dx dt gives you velocity. Why minus? Because if you see that it is slowly moving in this way, so the area is decreasing with time. Okay, so this was the area initially, after some time it will move over here, so area will decrease. So dx dt represents the negative of the velocity. Okay, so minus dx dt is the velocity, so we can write b into L into v. Okay, or induced EMF is b v L. Okay, induced EMF is b v L. Here you have to write v equals to minus dx by dt. Okay, use the negative sign, no problem, but don't forget to eliminate it. Final expression should not have any negative sign. Okay, so F7 equals to BVL. This is one of the most asked derivation for 3 marks. Okay, now, next, explain briefly the coil magnet experiment to demonstrate the phenomenon of electromagnetic induction. This is also a very common question asked in pre-board exam. Okay, so first of all you have to again draw the diagram. It is the easy question, that's why I have included it. Okay, a coil, a magnet with some flux lines linked with the coil. Okay, and the magnet is moving. When the magnet approaches the coil, the galvanometer needle deflects, indicating a current is induced. When the magnet is pulled away, the needle reflects the opposite direction, showing that the current reverses. No current is induced when the magnet is stationary with respect to coil. Okay, so magnet has to move towards or away from the coil. Okay, when it is moving, the galvanometer reflects. When it is moving away, the galvanometer reflects in the opposite direction. So if the magnet is moving towards the coil, galvanometer suppose deflects on this side. When the magnet is moving away from, then it will reflect in the opposite side. That has to be mentioned clearly in this statement. Okay, when the magnet is moving towards the coil, the galvanometer deflects, indicating a current induced. When the magnet is pulled pulled away, the galvanometer deflects in the opposite direction. So this is clear, this has to be clearly mentioned. Now what is the conclusion? A current is induced in the coil when the magnetic flux through the coil changes. This confirms Faraday's law of induction, and the direction of the current flow follows the Lenz's law, opposing the change in the magnetic flux. Okay, so both Faraday's law as well as Lenz's law can be explained from this observation. Now mention 2-3 uses of applications of Polaroids. Application of Polaroids are also very important question. Polaroids are used to control the intensity in sunglasses, window panes, etc. Polaroids are also used in photographic cameras and 3D movie cameras. They are used in 3D movie glasses as well. Mention Einstein's photoelectric equation and explain the symbols. Okay, so Einstein's photoelectric equation is h nu equals to phi plus half mv square. You can write in the opposite way also, half mv square is equal to h nu minus phi, whatever you are comfortable. So here you have to mention h is the Planck's constant, nu is the frequency of the incident light, phi is the work function of the metal, m is the mass of electron. Okay, if you know the values you can write it, otherwise you can skip it, not compulsory. V is the velocity of the ejected electron. Okay, V is the, actually it should be maximum velocity of the ejected electron. Write 3 features and properties of nuclear force. So the nuclear force is much stronger than the Coulomb force acting between the charges or the gravitational forces between the masses. The nuclear force between two nucleons falls rapidly to zero as their distance is more than a few femtometers. Nuclear force is also a short range force. The nuclear force between neutron-neutron, proton-neutron and proton-proton is same. So that means nuclear force is independent of charge. So these are the 3 features or properties. Both can be coming. Write 3 limitations of Bohr's atomic model. Okay, the Bohr model is applicable to hydrogenic atoms only. It cannot be extended to even mere 2 electron system, for example helium. While the Bohr model is correctly predicts the frequencies of the lights emitted by the hydrogenic atoms, the model is unable to explain the relative intensities of the spectral lines. The model does not explain the fine structure and splitting of the spectral lines observed under a magnetic field. Zeeman effect and Stark effect cannot be explained using Bohr's atomic model. What are coherent sources of light? Give one example. Okay, so coherent sources of light are light sources that emit light waves with the same frequency, wavelength and phase, or have a constant phase difference. So it can be 2 ways. One is the phase difference is constant, another one is phase difference, same phase difference. Okay, so for example, same phase, you are in class of 2026 batch, which will be passing out in 2026, right? So you are, all of your students batchmates are having a fixed phase relation, right? They are all at same phase. But the batch that already passed last year, they are 1 year ahead of you, and those students who are studying in PU1, they are 1 year behind you. So the phase difference between you and your previous batch is 1 year, and if you continue to study properly, the phase difference will still continue with them, right? And similarly, the batch which is ahead of you, the phase difference will still continue. Okay, so these are the example of coherent light. An example of coherent light is laser light. Okay, the laser light is one of the coherent sources. All the rays coming off a laser source are all coherent. State Huygens principle in wave theory of light. So as I mentioned, Huygens principle is also very important. Huygens principle states that every point on a wavefront acts as a source of spherical wavelets. The sum of these wavelets forms the new wavefront. Okay, so all points in a wavefront are the sources of secondary wavelets, and whenever you draw the Huygens theory, diagram is compulsory. Explanation of the diagram is not required, but at least draw the diagram, show the diagram. Give Einstein's explanation of photoelectric effect and write Einstein's photoelectric equation. Okay, photoelectric equation we have already done. Now Einstein's explanation we have to do. So Einstein suggested that each photon in the light have energy proportional to its frequency nu, given by E equals to h nu, where h is Planck's constant. When light shines on a metal surface, photons transfer their energy to the electrons in the metal. Okay, any energy from the photon exceeding the work function of become the kinetic energy of the ejected electron. So any energy which is more than the work function. Work function is basically the minimum energy required to free the electron. Okay, if it is excess than that amount, then electron starts coming out. How can a semiconductor diode be forward biased? What happens to the width of the depletion region when forward bias voltage is increased? A semiconductor diode is forward biased when you connect the positive terminal of the power source like a battery to the P side of the diode and negative terminal of the battery to the N side. Okay, so you have a diode, and if you connect the P side, that is P side, this is N side. If you connect the P side to the positive and negative with the N side, this is called forward bias. So when the current is trying to flow in the direction of the arrow, then it is called forward biased, and if it is in the opposite combination, then it is called reverse biased. Okay, this setup helps to overcome the potential barrier created by the depletion region and allows the current to flow through the diode. As you increase the forward bias voltage, the depletion region becomes narrower and slowly disappear. Okay, so what the question, what width of the depletion region with the forward bias voltage? So this is the explanation. Write three differences between intrinsic semiconductor and extrinsic semiconductor. Okay, so intrinsic and extrinsic, again definition. So try to write the properties. Properties gives you an idea to the teacher that okay, you are well prepared, and sometimes if your answers are well curated, then in some cases small mistakes can be ignored by the invigilator. Okay, your paper, your writing paper is the your best representation to the teacher. Okay, so teacher, whoever is checking your paper, should know that okay, the students who is writing this paper is well studied, they have studied throughout the year and they are deserving these marks. So that is one impression that you should make on your teacher. Okay, so property definition: a pure semiconductor with no impurities is intrinsic semiconductor. Extrinsic semiconductor are semiconductor doped with small amount of impurity to improve conductivity. Charge carriers, equal number of electrons and holes. Unequal number of charge carriers, majority carriers are electron or N type, holes in P type, and minority carriers. Conductivity, low conductivity at room temperature, high conductivity due to the doping, which increases the charge carriers. Give the Cartesian sign convention used to measure the distances and heights in spherical mirrors. So this is a 3-marker question. So you have to draw the diagram and you have to mention that any direction along positive x-axis is positive. So any direction along positive x-axis is positive, and any direction along the negative x-axis is negative. Any direction in the positive y-axis is positive. You have to write it in terms of words, and any direction in the negative y-axis is negative. Okay, if you write this, then you will get full marks with the diagram. Diagram is compulsory. Diagram is compulsory along with this. Any direction measured in the direction of positive x-axis is positive. Any distances measured in the negative x-axis is negative. Any distances measured in the upward direction is positive. Any distances measured in the downward direction or negative y-axis is negative. Also, you mentioned that the one more thing that you have to show here, that the location of the mirror or the lens is the origin. Now if same question is asked in case of lenses, instead of mirror you have to draw lens. Okay, don't draw mirror in if the question is asked about lenses. Everything else is same. Okay, if it is spherical lenses, then draw a convex lens. Remove this mirror and draw a convex lens, and the center of the convex lens should be your origin. Okay, clear? Show that the focal length of a spherical mirror is equal to half of the radius of curvature. This is also very important question. So here we have a ray of light falling on the mirror and it is reflecting back, passing through the focus. Okay, if the ray is parallel to the principal axis, it will always pass through the principal focus. Now if you join the center of curvature and the point of reflection, then that will give you the perpendicular. Okay, this is the normal, and normal means this is the angle of incidence, this is the angle of reflection. So angle of incidence should be angle of reflection, right? And the total angle, what is total angle? Total angle is 2 theta. If this angle is 2 theta, then this is the parallel, these two are parallel lines, this is the bisector, so this is an alternate angle. Alternate angle means this will also be theta. Again, these two are parallel and this is a bisector, so the alternate angle in this case is theta. Okay, so remember the diagram. Okay, remembering the diagram will help. Otherwise, practice the diagram 2-3 times if you don't understand what is theta, why is it is theta. So remember, this is angle of incidence, this is angle of reflection. From the law of reflection, angle of incidence is equals to angle of reflection, and thus the total angle will be 2 theta, and for this bisector, this 2 theta will come over here, and this 2 theta this will be theta based on this. Okay, now we have to take two triangles. To take triangles, we have to first draw a perpendicular on the principal axis. MD is the perpendicular on the principal axis. Now we have to take two triangles, triangle MDC, triangle MDC, and from here we will get tan theta. What is tan theta? Tan theta is perpendicular by some people have curly brown hair turned permanently black, so perpendicular by base, so MD by CD. Okay, tan theta is MD by CD. Okay, now for small paraxial rays, paraxial means what? Paraxial means this point M is very close to the center of the mirror. So those are called paraxial rays. Our entire ray optics is based on paraxial ray. Okay, because mirrors are not that big, mirrors are small usually, right? So for paraxial rays you can apply all the formulas, all the laws that we have learned. Okay, so for paraxial rays this point is very close to this, and we can say that this distance dp is actually 0, so d and p are almost same, and the angle theta is very, very small. Okay, so theta is very small and d is almost at P. Okay, so this point D is actually very close to point P. So now let us write the equation again. So tan theta can be approximated as theta equals to MP by CP. Okay, MP by CP. So what is CP, by the way? CP is our radius of curvature, so we can write theta equals to MP by R. Okay, R is the radius of curvature, CP is radius of curvature. Right, so this is very basic. Now next we will take another triangle. Which triangle we will take? We will take the triangle obviously MFD. From triangle MFD we can write tan 2 theta. Now for this triangle tan 2 theta, okay, and that will be obviously MD by FD, MD by FD, and similarly for paraxial rays what we can write? We can simply write 2 theta equals to MP by FP. Now what is FP? F is focus, this is the pole, so FP must be the focal length, so this can be written as MP by F. Now this was our equation number 1. This is our equation number 2. So if we divide equation number 1 with equation number 2, what we will get? We will get on our left hand side theta divided by 2 theta equals to MP by R divided by MP by F. Okay, so F will be goes up, R comes down, MP cancels, theta cancels. So from here we can write F equals to R by 2. Okay, this R will come over here. So F equals to R by 2. This is the derivation that we are trying to prove. So hence prove. Okay. So when I was a kid, I used to love write this proved, hence proved. Okay, so that was one of my favorite thing to do. Now this is a very interesting derivation. Practice it. It is very common in your pre-board exam, right? Write the two conditions for total internal reflection of light and mention its one technological application. So light must travel from denser medium to rarer medium. The angle of incidence must be greater than the angle of critical angle between the medium. Application: optical fibers or cables are used to transfer data using total internal reflection. Now from now on we will be doing all the derivations and numericals. Now let us move on to the derivations. State Gauss law in electrostatics, or you can say Gauss's law in electrostatics. Derive an expression for the electric field at a point due to an infinitely long uniformly charged straight wire using Gauss's law. So Gauss's law statement: the total electric flux through a closed surface in air is 1 by epsilon naught times total charge enclosed by that surface. So E dot ds, close integral E dot ds is equals to Q by epsilon naught. So this is very, very important. Remember, whenever you are writing Gauss's law, you have to write the equation as well. Also, this question as a state and explain Gauss's law can be asked as a 2-marker separate question as well. Now in this chapter, in the electrostatics chapter, electric charges and field chapter, we will do 3 derivations, very, very important derivations. So let us start. First we will be doing the electric field due to a straight conductor, infinitely long charged conductor. So it's a very long conductor, obviously it is extended both sides. Now we are trying to find electric field at some distance, say at a distance r. To find the electric field, what we have to do? We have to construct a imaginary Gaussian surface. Gaussian surfaces are always imaginary, and it will be a cylindrical Gaussian surface. Okay, we are trying to find, say, electric field at this point P. So this, so what I have done some cheating. The cheating is, first should be, you should denote this distance r, then you should construct the cylinder based on that. But because we do not know how the cylindrical surface will look like, that's why I have drawn the cylinder first, then I have shown this is the distance. Clear? So this distance is important, and based on this distance we are drawing the cylinder, so that the radius of this cylinder is also the same distance on which we are trying to find the electrical field. Now imagine the length of the cylinder to be L. This is again imaginary, right? Now this is charged, right? This is a charged line, right? This is also called line charge. These are also called line charge. Now for a line charge, what is important is charge per unit length or line charge density. The line charge density in this particular case, say lambda. Now we are going to apply Gauss's law. So first of all, obviously surface we have considered. Okay, electric field is radially outward from the line. No electric field line going in this direction or in that direction. Why so? Because of symmetry. Okay, this is only symmetry is the electric field lines should go away from the positive charge. Based on that, we can say that electric field lines are only going along the curved surface of the cylinder, not along the flat surfaces of the cylinder. Okay, now what? So first thing is the to calculate the charge enclosed. How to calculate charge enclosed? Charge enclosed can be calculated in this cylinder, what is the charge enclosed? The charge enclosed is line charge density times the length of the cylinder, right? So how much charge is enclosed in the cylinder? Obviously this much, right? So what is line charge density? So for unit length, charge is lambda. So total length is L. So charge enclosed will be lambda into L. That is the total charge enclosed in the cylinder. Now total charge enclosed we have calculated. Now next what? We are definitely trying to apply the Gauss's theorem, which states that closed integral E dot ds equals to Q enclosed by epsilon naught. That is lambda L by epsilon naught. Now what? Now because of the symmetry of this arrangement, symmetry means no matter where you look, okay, it always appears to be same, because it's a very long wire and cylinder, you can rotate the cylinder along the axis. So this is the axis of the cylinder. So if you rotate the cylinder like this, okay, it will not change anything. That means what we can say that because of symmetry, electric field is constant on the surface of this cylinder, magnitude wise. So we can write this as E into closed integral ds equals to lambda L by epsilon naught. E is constant on the surface of the cylinder due to symmetry. Derivation wise, it's very simple and easy derivation. Now as I mentioned, we will only take the curved surface, not the flat surfaces. So what is the surface area? Surface area of a cylinder is given by 2 pi r L. Okay, surface area of a cylinder is given by 2 pi r L, right? 2 pi r is the length and L is the height. So 2 pi r L is the total surface area, equals to lambda L by epsilon naught. Now if you see that L getting cancelled, so we get E equals to 1 by 2 pi epsilon naught lambda by R, right? We can reorganize this slightly, 1 by 4 pi epsilon naught. It's not necessary, you can leave the answer in the previous stage as well, but this one looks better because 1 by 4 pi epsilon is the constant. So that's why we have kept it like that. Now let's move on to the next question. Derive an expression for electric field at a point outside a charged spherical shell using Gauss's law. Again, this in this question also they might ask state and explain Gauss's law, and then they might ask this question. So Gauss's law is common, and based on this, these are the two applications that is very, very important. Now in this case, we have a spherical shell. Spherical shell means it's like a shell of egg, covering of the egg. Okay, shell means covering of the egg. Okay, hard and nothing inside. Okay, only the egg cover is there, inside the egg is empty. That can be considered of a shell. For example, the plastic ball that you used to play when you were kids, right? The heavy plastic balls, inside the ball was empty, but outside was heavy. So that's you used to play cricket with that, right? All of us played. So that is also an example of a shell. Okay, this is the cover, inside is hollow. Now if you want to charge this, where the charges will stay? Charges will always stay on the surface, right? Charges will always stay in the surface. Charges cannot stay inside because it's a shell. So if you apply Gauss's law, Gauss's theorem inside the shell, okay, charge enclosed will be 0. So charge enclosed inside the shell is 0. So electric field is 0. So charge enclosed is 0, that's why electric field is also 0 inside. So in case they ask find the electric field inside as well as outside, so inside you don't have to do anything, inside you have to just mention that charge enclosed is 0, that's why electric field is also 0. Now if you want to find the electric field at a distance, say small r, again the same method, we have to construct a Gaussian surface, and in this case the Gaussian surface is a sphere. Gaussian surface is a sphere of radius small r. Okay, so we have constructed a Gaussian surface. The total charge, say, is capital Q. Total charge enclosed, in this case, say capital Q. Try to draw this Gaussian surface as well as everything using a proper compass, so that the circles look same, right? I have drawn it in using my hand, so maybe slightly shifted on that side. Okay, so now this is our distance r. Radius of the sphere is capital R. Remember, this is for condition outside the shell, means r should be greater than that of r. Okay, for r less than r, this is r less than r. Okay, so this is the case. Everything is written in the diagram itself. Now for r greater than r, again, what is Gauss's law? E dot ds equals to q enclosed by epsilon naught, or it will be equals to q enclosed here is capital Q by epsilon naught. Right, now what? Now what we will be doing, we will again say that due to symmetry electric field is constant. Due to symmetry electric field is constant on the surface of S. What is S, by the way? S is this one. This surface we are naming it as S. Okay, so therefore E close integral ds equals to q by epsilon. What is close integral ds? By the way, we have done it last problem also, this problem also. Close integral ds represents basically the surface area, total surface area. Close integral means total surface area. For a cylinder it was 2 pi rl, for a sphere it will be 4 pi r square. Okay, simple formula of surface area, 4 pi r square equals to q by epsilon naught. So from here you can calculate electric field. E equals to 1 by 4 pi epsilon naught q divided by r square. Okay, so this is the formula for electric field on the surface outside the charged spherical shell. Easy derivation, very easy derivation. Derivation wise not difficult. Okay, just need to remember the steps and everything is super simple and easy. And this derivation might come on your pre-board as well as your board exam. Both way it is important. Now derive the expression for electric field at a point on the axis of a dipole. Now axis of a dipole is more important than the on the equatorial plane, but equatorial plane might also come. In this lecture I am going to discuss only on the axis on the of a dipole. If you want equatorial plane, I have already done a video on electric charges and field, entire chapter on our Brahmastra series. You can go and check that out. Okay, but for pre-board this is most important, so don't forget to practice this one. If you do not have at least enough time, this one is the super important. Okay, the equatorial plane also has came in the past, and some of the districts might give that as well, but this is the most important one. So if I have to choose, 80% is this one, 20% are that one. Okay, so that's why I am not giving that question again. So if you are interested, you can go and check that, check my Brahmastra series where I have discussed everything. Now let's move on. So suppose we have charges minus q plus q. The distance between the charges is say 2a, and we are trying to find electric field at a distance at a point P. The distance of the point P from the dipole is given by r. Okay, the distance of the dipole is always measured from the center of the dipole. Remember that distance of the dipole is always measured from the center of the dipole. This is A, this is also A. Okay, now what we have to do, we have to find the total. First of all, we have to find the electric field due to individual charges at this point, and then we will apply superposition principle to calculate the total force. So what are the two forces acting on this? First of all, obviously F plus, and secondly F minus. Okay, now negative charge what is the direction of electric field due to negative charge? The direction of electric field due to negative charge is always towards. What about positive charge? Electric field due to positive charge is always away from. Okay, so this is F plus and this is F minus. Now we have to calculate them individually and then add them. That's it. One mistake I made. It is E plus E minus. Okay, so E plus and E minus. So what is E plus? Electric field. What is the formula for electric field due to a point charge? Electric field due to a point charge is very simple. KQ by R square. Right? KQ by R square, and it is along away from P. Okay, and E minus is given by KQ again by R square towards the dipole. Now here, even though I have written R, those two R's are not same. Okay, away from the dipole is better. It is away from the dipole towards the dipole. That is better. Now even though I have written R square, both cases R's are different. Okay, what is the difference in R? So for positive charge, this is actually the R. Okay, this is actually R. So what is this distance? The total distance is R. This much distance is A. So this small distance must be R minus A. So this will be R minus A, right? R minus A. And what about the distance from negative charge? Distance from negative charge must be is given by, this is A, this is minus Q, so this should be R plus A. R ends over here, so here we have small a, so R plus A is the distance from negative charge. So here it will be R plus A. Now if you see that plus and minus, plus has a smaller denominator compared to minus, so plus is bigger than minus. So net electric field, the net electric field will be E plus minus E minus. Okay, so whenever you are solving problems related to electric field or cases where you are finding the net electric field, remember that do not put the sign of the charge in the equation. Determine the direction, and based on the direction whether they will be added or subtracted, you have to do that. Okay, here it has to be subtracted because they are in the same direction, they are in the opposite direction. Okay, so E plus is KQ by R minus A whole square, and E minus is KQ by R plus A whole square. This minus is not because this is minus, this is because of the direction. Now take the KQ common. This is very, very helpful for solving problems also. KQ as common. Now multiply the denominators. R minus A whole square, R plus A whole square. This will come over here. R plus A whole square minus R minus A whole square. Right? So now simplify this. KQ. So A square, A plus B whole square minus A minus B whole square. So there is a shortcut formula for that. Okay, so A plus B whole square minus A minus B whole square is equal to what? Equals to 4AB, 4R into A, divided by, and here if you take this whole square common, if you take the whole square common, what you will get? You will get R minus A into R plus A. What is R minus A into R plus A? A plus B into A minus B, that is A square minus B square. So it will be R square minus A square. Clear? Now what we will be doing, just we need to reorganize this. So E net is now given by K into 4R, not 4R, let me reorganize it, 2R 2Q into A. So we have broken this 4 into 2 into 2. 1, 2 we have kept outside, 1, 2 we have kept inside. Why? Because 2qa is a very well-known quantity for us, r square minus a square to the power 3 to the power square. We know that 2qa is what? Is dipole moment, right? So we will substitute that in this equation. So we get k into 2r into p divided by whole square. Now we will do one approximation. What approximation? Till this stage no approximation. Approximation will come after this, once you have substituted 2qa with p. Okay, now we have to substitute approximate that r is very greater than a. Okay, so r, distance r is much bigger than this dipole, distance between the dipole, because the definition of dipole states that the two charges, two equal and opposite charges separated by a very small distance. So this distance 2a is small, that means distance a will also be small, right? So r must be greater than a. So what we can say that net, E net is given by k into 2r into p divided by r to the power 4. Okay, so we have approximated r square minus a square to be r to the power of 4. Okay, so we can cancel this and we can get 2kp by r cube. Okay, one of the r's cancelled, so we get 2kp by r cube. Now it's time for us to put the original value of k. So E net becomes 1 by 4 pi epsilon naught p by r cube, right? So this is the net electric field. You can put the vector sign over here, and electric field and dipole moment are in the same direction. So vectorially you can write this as E net vector is equals to 1 by 4 pi epsilon naught 2p vector divided by r cube. Okay, in equatorial plane, instead of 2 there will be only p by r cube and it will be negative sign. You have to practice that. This one is more important. This one came more times in the past compared to the other one. That's why we have only covered this one. Okay, and if you want to solve the equatorial plane one, please don't forget to watch our Brahmastra lecture. Now next, define electrostatic potential due to a point charge and arrive at the expression for electric potential due to a point source charge. So what is the electrostatic potential? Electrostatic potential is the work done to bring a unit positive test charge from infinity to a point in electric field is the electric potential at that point. Right, this is the definition of electrostatic potential at any point. Now we have to find the expression for it. Now this derivation is very popular in pre-board again. So here we have a point charge, say plus q, and we are trying to find the electric potential at some point, say P. Now to find the electric potential at this point, we have to extend it and we have to go to infinity. Okay, we have to bring a unit positive charge starting from infinity to the point P and calculate the work done. Now infinity is something which is beyond our control. Obviously infinity is bigger than anything that you can imagine. So infinity, obviously something tricky. So what we will be doing, instead of going to infinity, we will take some intermediate point which is neither infinity nor our destination. This is our destination, infinity our starting point. So infinity say is Delhi and our ending point is Bangalore. So we started from Delhi, we are coming to Bangalore, but Delhi is very far away. So what we will take, we will do some intermediate stations, say around Gulbarga or Yadgir, somewhere around Karnataka region where it is around our reach. Okay, so say A and B. Okay, now this positive charge will try to repel the charge, repel the unit test positive charge. Okay, so suppose this is our test positive charge, not +1 but unit but test charge. Okay, so we are trying to bring a test charge. It started its journey in Delhi, but we don't care about that. We have reached our intermediate station, which is say Kalburgi. Okay, and from Kalburgi to Yadgir, how much time it is taking, we are trying to find that out, for example. So we will try to find the work that we need to do to travel from B to A, and the distance between them is very small, which is given by dx. Right, now the distance dx is very small compared to the entire journey path, okay, and compared to this r as well. So we can assume that electric field due to this charge is constant around B. So what is electric field at this point B? Electric field at point B is given by K Q by x square. X is the distance of this point from the source charge. This is source charge. This is called source charge. This is called test charge. Test charge does not have their own electric field. Source charges, they are the creator of electric field as well as electric potential. Okay, so this is the distance of the point B. So the electric field at this point is kq by x square. So if you keep this charge over here, what force it will experience? It will experience as a force is given by q into EB. Right, force is given by charge into electric field, which is nothing but K capital Q small q by x square, Coulomb's law. Now this is the force which is experienced by this charge due to the source charge. Now if you want to move this charge from B to A, then you have to apply an external force. You have to apply an external force, and that external force must be in the opposite direction of this internal force. Okay, so it should be minus F, okay, because it should be opposite, and that means it should be minus K capital Q small q by x square. This much force you have to apply. Now if you are moving this charge from B to A, what is the work done? The work done to move it from B to A is given by the external force that you have applied into the displacement. Work done is force into displacement, old formula from your Q1. So work done we have calculated. Now this is only for small work done to bring it from B to A. Now we have to extrapolate this equation, and we have to start at infinity and come back to our destination. Okay, so the total work done is given by integration of the small work done. Starting point is our infinity, ending point is at a distance r. Okay, now we will simplify this one by one. Now first we have, obviously you have to put that external force value over here, minus K capital Q small q divided by x square into dx. Don't forget the negative sign. Negative sign is very important, otherwise you will miss out. Also mention that if external is equals to minus f, that's why it is negative. If you do not mention it, 1 mark will be deducted. Right, now let's try to simplify this. Infinity to r. Now we will put this value, minus k q by x square dx. Now out of all these terms, k is a Coulomb's constant, q is charge which is constant, small q has taken by us, so this is also a constant. So only thing that is changing is x. So minus k small q capital Q integration infinity to r dx by x square. Now at this stage I hope you are already aware how to do integration, and this is one of the very simplest form of integration. So we can write w equals to minus k q into minus 1 by x infinity to r. Okay, minus 1 by x is the integration of this. Right, I have not explained why this is right, right? So I hope you have done integration properly. When you learn this concept at the beginning of your year, okay, many of you have trouble that understanding why, sir, what is integration, what is this. Now integration, I generally tell my students that at the beginning of the year you are feeling this is difficult, but at the end of the year when you revisit this concept, you will think, oh, what a joke, we are afraid of this kind of integration, right? These are the one of the simplest integration. Now, so this is 1 by x. So minus can be taken common, minus minus plus. So we get k small capital Q small q. And now first of all we have to put the upper limit, that is 1 by r, minus 1 by lower limit, that is 1 by infinity. This minus already taken care of as a common. Okay. So now k capital Q small q by r. This one is 0, 1 by infinity is 0, right? So this is the work done. Now this is not yet done. So what is potential? They have not asked you to calculate the work done. They asked you to calculate the potential. Potential is work done per unit charge. So you have to divide it by small q. Work done per unit test charge. So that is k capital Q by r. Or potential is, now let's suit it up, let's give it a formal look. So formal look means it has to wear the tie and bow, right? Looks good, it cannot be casual anymore. So this is the electric potential, 1 by 4 pi epsilon naught q by r. Easy derivation again. This came in 2025 exam, so this derivation coming in your final board exam is less. But do not ignore this derivation, because PU board has tendency of repeating questions back to back years. Okay, PU board has a tendency of repeating questions back to back year. So this question might be repeated again in 2026. Okay, so if you ignore this thinking that it already came in 2025, don't do that. It is not only important in your board, it is also important in your PU2 final board exam. Now, obtain an expression for potential energy of an electric dipole placed in an uniform electric field. This is also possible. This kind of questions also has come in the past. Define energy density of a charged capacitor. How the energy density related to the electric field present between the plates of the capacitor. Okay, so let's see. So first we will do is expression for potential energy. This is not the expression for electrostatic potential. Electrostatic potential for a dipole never came in board exams. It did came in some of your college exams, but because your pre-board exam paper is coming from district administration, so there is a less chance, very less chance of coming that electrostatic potential due to a dipole. Electrostatic potential due to a dipole is completely different derivation. Here we are doing the electrostatic potential energy due to a dipole, okay, in an external electric field. So we have external electric field and a dipole is placed. This derivation, first one, can be asked as a 3-marker individual derivation as well, small. So here we have a positive charge, here we have a negative charge, and we know that. So the force on the positive charge will be along the direction of the electric field. Force on the negative charge will be opposite direction of the electric field. And what will it will experience? It will experience something called a torque. We have already done the derivation, right? And what is the expression for the torque? It's very essential to remember the expression for the torque. Sine theta. PE sine theta is the torque that is experienced by this dipole. Now, if the angle is theta, obviously, if you displace this dipole by a very small angle, say delta theta or d theta, okay, what will be the work done to rotate this dipole by this small angle d theta? The work done is given by, to rotate it by a very small angle, the work done is given by tau into d theta. In case of normal force, linear force, okay, it was force into linear displacement. In case of angular force, that is torque also is called angular force. For angular force, it is angular force into angular displacement, that is d theta. So this is the small work done, and that is given by PE sin theta d theta. Okay, now what? Now we have to calculate the total work done. Total work done to rotate it, say from an angle, we will start at an angle 90 degrees, okay, to the angle theta. So our starting angle is pi by 2 and our final angle is theta. Okay, so total work done to rotate it from an angle pi by 2 to theta. Why we are choosing pi by 2? You will see that in a while. Okay, so total work done to rotate it from pi by 2 to theta is given by integration pi by 2 to theta dw, that is pi by 2 to theta PE. So it is very difficult sometimes to remember, right? So I will give you a hint how to remember it. Now if you see that P is constant for a given dipole, electric field is obviously uniform electric field is constant, so P and E will be out of the integration. We will only leave with pi by 2 to theta sin theta d theta. Now what is the integration of sin theta? Integration of sin theta is minus cos theta. Okay, cos theta's differentiation is minus sin theta. So now cos is taking revenge. So cos is saying that, well, when differentiating me, you got negative, you made me negative. Now while integrating sin, I will come as a negative, right? So now we will see that PE cos theta with the limit of pi by 2 to theta. Now the limit is from pi by 2 because we don't want to have anything added to it, okay? So we don't want to have anything added to the extra term. So pi by 2, starting pi by 2 means potential energy at pi by 2 becomes 0. That's why, nothing else. So work done is given by minus is common now. This minus sign is common. So we got cos theta minus cos pi by 2, right? Cos pi by 2 equals to 0. So we simply have this as work done is given by minus PE cos theta. Now this work done will be stored as potential energy of the dipole. Potential energy is denoted by symbol U. So potential energy of the system will be stored because the work is being done. So that means the potential energy of the dipole will be minus PE cos theta. Okay, so this is the expression for potential energy due to dipole. Now one more question was there, that is define energy density of a charged capacitor. How is the energy density related to so energy density of a charged capacitor? This is part A, main question. Part B, a side question is here. So that is energy density. Now energy density is denoted by a symbol small u, which is which gives the total energy divided by volume of the capacitor. So total energy, or we can say that not total, let's say that energy stored per unit volume is the energy density of the capacitor. So energy density means normal density, mass density means mass by volume. Energy density is energy by volume. What about relation with the electric field? It is given by half epsilon naught E square. Okay, so energy density is proportional to square of the electric field, and we can say that the energy in a capacitor stored between the plates in the form of electric field. Okay, so when you are charging a capacitor, the charges gives rise to a electric field between the plates, and that's how the charge is the energy is stored in the capacitor. Now next question, define okay, the energy density so this is already written over here. The energy density U of a charged capacitor is the energy stored per unit volume of the electric field between the plates. So U equals to total energy stored by volume. Okay, so I think I have already written it, so no need to explain anymore. And U is equal to half epsilon naught E square. Next, move on. Derive an expression for effective EMF and effective internal resistance of two cells of different EMFs and internal resistance connected in series. So basically it's a cells in series. So we will be doing both cells in series as well as cells in parallel. Both are important. So two cells, say epsilon 1 R1, epsilon 2 R2, they are connected in series. Series means one after another, and they are connected across a resistance R. Okay, so irony is when we are trying to see that when the capacitors are in series or parallel, or in case of resistors in series and parallel, even though I have not done it in this particular lecture, we use a battery. Now when we are saying that cells are in parallel, we use a resistor. Resistors remain same. So equivalent circuit will be having only one battery or one cell. Okay, so this is epsilon equivalent, this is R equivalent, and the external resistance remains the same. Okay, so we have to find this epsilon equivalent and this. Now what is the meaning of this equivalent circuit? That means if the current in the circuit was I, same current will be there in the circuit as of now. Now as I mentioned, in series combination current remains constant. In parallel combination, voltage remains constant. Now here the current is constant, so same current is flowing through all the components. So we will simply apply Kirchhoff's laws. Okay, and Kirchhoff's law says that if we are going in the direction of the battery, so what we will be doing, we will say that I into R plus I into small r1 plus I into small r2. Same current, remember whatever current is exiting the battery, same current should come back to the battery as well. And same logic, with the same logic we will say that the resistances R1 and R2 are also subjected to the same current I, and obviously the total current in the circuit is I, means capital R is also having the same current, and that is equals to epsilon 1 plus epsilon 2, right? Applying Kirchhoff's laws. Okay, Kirchhoff's laws we know, so we can simply apply Kirchhoff's laws. That is the easiest part, right? Now what? So now we will be trying to find either we can find this current, or what we will be doing, we will take this I R1 plus R2 equals to epsilon 1 plus epsilon 2 minus IR. Okay, or capital I equals to, this is a trick that you have to remember, epsilon 1 plus epsilon 2 divided by R1 plus R2 minus I into R divided by R1 plus R2. Okay, this is a trick that you have to remember, how to organize the equation. We are not taking all the R's common, but we are doing it in this way. Now what? Now we will be doing the same for the equivalent circuit as well. For equivalent circuit, what we can write is that IR plus IR equivalent equals to epsilon equivalent, right? Here we have only two resistors, R and R equivalent, so current is same. So from there we can say that, okay, so I into R equivalent equals to epsilon equivalent minus IR, or from here we can say I equals to epsilon equivalent by R equivalent minus I into R by R equivalent. Now we can easily compare these two equations, 1 and 2. This is 1, this is 2. So if you compare these two equations, we will see that I is same on the both cases. One case we have epsilon 1 plus epsilon 2, and another case we have epsilon equivalent. So we can simply say that comparing comparing 1 and 2, we can say 1 and 2, obviously epsilon equivalent is epsilon 1 plus epsilon 2, and R equivalent would be, so epsilon plus epsilon 2 is epsilon equivalent. From the division we can say that R equivalent, also we can verify it from this equation also. Okay, so we can say that R equivalent is R1 plus R2. Okay, so in series combination is same as resistance is in series, this simply gets added. Okay, where resistances gets added, EMFs also gets added. Derive the expression for effective EMF and effective internal resistance for two cells of different EMFs and internal resistance connected in, this one will be parallel. This is not series, this will be parallel. Okay, so now we will be doing the same thing, but here now the EMFs are connected in parallel. So this is slightly trickier than the previous case. Okay, slightly trickier than the last case. So don't ignore, both derivations are important. Now here this is epsilon 1 R1, this is epsilon 2 R2, and the entire combination is connected across a resistance, external resistance R. What will be the equivalent circuit? As usual, equivalent circuit will be same, which will only have one cell, the resistance will be same. So in this case, suppose the total resistance is I, the same current will be maintained as well. Okay, so only one condition for equivalent circuit, the total current in the circuit, total voltage should be same. Now here individual currents are not same. Here say current is I1, it will be I2. Okay, so individual currents are not same in this case, and we have to take them separately and try to figure it out. So first of all, we will take the outer loop. We will take the outer loop and apply the Kirchhoff's law. So Kirchhoff's law says that, so whatever current goes out, same current should go in for a battery. So I1 current is going in, but I current is passing through R. First of all, what is I? I is simply I1 plus I2. So if we can find I1 and I2, we can calculate I. So for the first loop, including epsilon 1, what is the current through R1? Current through R1 is I1. So I1 R1 plus current through this capital R is I. So I into R equals to epsilon 1. So go through a complete loop, add all the currents and corresponding resistances, current times resistances, right? If you are going in the same direction, they will always add up, and that should be equals to the EMF. That is the Kirchhoff's law. So from here we can calculate I1. So I1 R1 equals to epsilon 1 minus IR, or I1 equals to epsilon 1 by R1 minus I into R by R1. Okay, similarly, so we can do that similarly because it's almost same. So similarly, I2 will be equals to epsilon 2 by R2 minus I into R by R2. Now add these two. So if you add these two, what we will get? I equals to I1 plus I2. That is, we get epsilon 1 by R1 plus epsilon 2 by R2. Now the problem here is not this one, problem is this one, I into R by R1 plus R by R2. right? This one is something problem. Last case it was same, so we had no problem. So what we will be doing, we have to simplify this little bit more. So we will keep that as IR. Remember, this IR we will try to keep it as IR as much as possible. Okay, so what we will be doing, we will divide everything by this R1 by R1 plus 1 by R2, everything. So we get on the left hand side I divided by 1 by R1 plus 1 by R2 equals to epsilon 1 by R1 plus epsilon 2 by R2 whole divided by 1 by R1 plus 1 by R2. We are dividing every term with this 1 by R1 plus 1 by R2. So what we have in this case, we have minus IR, right? Because this portion is divided, so this cancels, right? So if you want, you can write that over here 1 by R1 plus 1 by R2 was already there, and because we are dividing each and every term, so it will also be divided by 1 by R1 plus 1 by R2. So 1 by R1 and divided by 1 by R2 will cancel. Okay, that's why we have not written it, we simply ignored it. Right, now we will do the same for the equivalent circuit and try to compare. So this is my equation number 1. Now for equivalent circuit, current is I, equivalent resistance is R, external resistance is capital R. So we can say that epsilon equivalent must be equals to I R plus I into R equivalent, right? Or I by what we will be doing, we will be doing something here, I into R equivalent equals to epsilon equivalent minus IR. So I just written, generally I write the voltages on left hand side, epsilons on the right hand side, left hand side, but here I have just switched the sides, that's it. Okay, don't worry, why sir you have written it like this? So let me correct that if you are wondering. So for this, voltage drops are I into R and I into REQ, and that should be equals to the EMF that is connected in the circuit, that is epsilon equivalent. Okay, now clear? Now we will slightly reorganize it. I by 1 by R equivalent. So this came down as a division of 1 by R equivalent. Okay, because we have to match this minus IR. So if we can match this, we will get whatever are the R epsilon equivalent and whatever is the R equivalent. So to match this equation, we have basically keep it as 1 by R equivalent, right? So now see, if you compare these two equations, obviously epsilon equivalent is clear. This is my equation number 2. Comparing, we can write epsilon equivalent must be equals to this entire thing. So that is epsilon 1 by R1 plus epsilon 2 by R2 divided by 1 by R1 plus 1 by R2. So this is the entire epsilon equivalent. What about R equivalent? So if you compare this one and this one, we will say that 1 by R equivalent is 1 by R1 plus 1 by R2. Okay, this derivation is not easy. You have to practice it to get a hold of it. This derivation is not easy. If you don't practice it, you will forget in the middle of the derivation what should be the structure, how to organize it, how to simplify it. So please practice this 2-3 times. This derivation is one of the important derivation for your PU2 pre-board. Next, obtain the balancing condition of Wheatstone bridge using Kirchhoff's law. One of the most asked question again. Now this question came in 2025 exam. So there is a chance that cells in series or cells in parallel might be coming. No guarantees as again, okay, because PU board tend to repeat questions. So if they are repeating it, well and good, this is one of the easiest derivation. If not, then definitely you should practice the other two as well. So now here we have P, this one is Q, this one is R, this one is S. P, Q, R, S. Okay. So this is a voltage source V, not required anyway. Now what is the condition for balance? So suppose the current through the current through this say I1, current through this say I2, current through this IG. Okay, now balanced condition is this current should be equals to 0. For a balanced Wheatstone bridge, now if you are not sure about the spelling of Wheatstone, number one, it is wheat, that is the crop that we use for making rotis. So wheat and stone, the stone which is used to grind the wheat. Okay, this is a surname of a person, Wheatstone, and secondly it will be given in the question as Wheatstone, so don't mistake the spelling. It will be given in the question paper, so in case you are not sure about the spelling, make sure you read the question paper and write it down. Okay, or else you can remember it like wheat and stone. There is no space, Wheatstone is single name. Now why the surname, don't ask me, I don't know. Now Ig equals to 0, so whatever current I1 is passing through this, so current through P and Q should be same. So therefore current through P and Q should be same. Should be same. And what is that value here? We have denoted it by I1. Similarly, current through R and S should also be same, and that is given here as I2. So because there is no current is passing through the galvanometer, so no current is getting added here or subtracted here, right? So that is the Kirchhoff's current law. Okay, Kirchhoff's current law says that whatever at a junction, whatever current is going out, that should be sum of the current. So here, because no current is passing through the galvanometer, we can say that whatever current is passing through P, same current should pass through Q as well. Now we will be applying, suppose A, B, C, D. We have to name them as well. We will be applying Kirchhoff's voltage laws or Kirchhoff's loop rule across A, B, D, A and B, C, D, B. Okay, these two loops we will be taking. So applying KVL in the loop, this is symbol of loop, A, B, D, A. So A, B, D, A means, why we are writing it like that? We are starting from A, we are going to B, we are coming back to D, and again we are closing to A. So if you are writing a loop, the starting and ending should be same. A, B, D, A. This is a symbol of loop, the path you have taken. Now if you take this loop, what is the voltage drop across any resistor? As I mentioned, voltage drop across any resistor is the current that is passing into the resistance. Here resistance is given by P. Now in this particular case, you are going through the galvanometer. Now current through the galvanometer is 0, so it should be 0. 0 into anything is 0. Now when you are going from D to A, you are going against the direction of current, because total current in the circuit is going in this direction from positive to negative. So current should branch out like this, right? So when you are going from D to A, you are going against the direction of current. So it should be minus I2 into R. And is there any battery connected in this loop? No battery is connected. Battery is connected outside the loop, but not inside this loop. So this should be equals to 0. That's how we apply Kirchhoff's voltage law, right? So I1P equals to I2R, or P by R equals to I2 by I1. Okay, now applying KVL in loop BC DB. BC DB. So what is the current through from B to C? I1 into Q. So voltage drop is I1 into Q. So I1 into Q. Now when you are going from this C to D, when you are going from C to D, again you are going in the opposite direction of the current. Opposite direction of the current means it will be negative, minus I2 into S, and when you are going from D to B, there is no current, that means it will be 0. Okay, and that is again equals to 0. Why? No battery is connected again in this loop. So no battery connected means it should be equals to 0. So we can say that I1Q equals to I2S, or Q by S equals to I2 by I1. Okay, so this is my equation number 1, this is my equation number 2. If you see, both equations on our right hand side are same. So I2 by I1, I2 by I1. So their left hand side should also be same. So comparing 1 and 2, 1 and 2, we can write P by R should be equals to Q by S. Right? If their right hand side is left hand side is same, right hand side should also be same. Right? Similarly, right hand side is same means left hand side will also be same. So now just rearrange it. P upon Q equals to R upon S. Cross multiply. P, Q and R exchange their positions. So this is the condition for balanced in a Wheatstone bridge. P by Q equals to R by S. This is the easiest and shortest derivation of this, and if you do that you will get full marks. Now next, derive the expression for magnetic field at a point on the axis of a circular current loop. This is also came in 2025, I think, I don't remember, but this is also one of the most important derivations. So here we have a circular loop and we have to find the magnetic field at a distance x from the center. Suppose this is the point we are trying to find the magnetic field. Say this is P, this distance is given by x. Okay, and the radius of the circular loop is given by capital R. Radius of the circular loop is given by capital R. Now to do that we have to construct a small current element dl, and we have to find the magnetic field due to this element dl at this point P. So the distance here is smaller from this current element. Distance will change based on where you are taken the current element, right? So the angle between this is 90 degrees. Okay, this angle and the angle between this, they are tangential, so it will be 90 degrees. Okay, so this is R distance. So what is smaller? This is a 90 degree angle. So this is R, this is X, so it should be equals to capital R square plus X square. Okay, we will use it at a later time. Now the magnetic field due to this will be, suppose this angle is phi. Then magnetic field at this point will also make an angle phi with this axis. Okay, this can be proven in geometry. I am not doing that. You don't need to do as well, but you have to remember that this top angle should be equals to this angle phi. Now also, if this is the magnetic field dB, why we are writing dB? Because this is due to a small element dl. We have to integrate it over the cycle to get the total magnetic field. Now this dB will have two components, one along the y, one along the x. Okay, so this is dBx. Now dBy, due to symmetry of the circle, dBy will be cancelled, but because if you take a same element in the diametrically opposite point, then dl, due to dl, this will be on other direction, so yy will cancel. So if the symmetry is there, one component will always cancel, remember that. And because of the symmetry here, y component will be cancelling, only x component will remain. Okay, so you have to mention due to symmetry y components will cancel. Okay, now we have to just find the dBx's and add them. So how to do that? So dB x is basically, what is dbx? dbx is db cos phi. dbx equals to db cos phi. Why? This is phi. This must be the adjacent component. Adjacent component are always cos. Now what is dB? For that we have to go back to our Biot-Savart's law, which states that magnetic field due to an element is given by 1 by 4 pi epsilon naught I dl sin theta divided by r square. Now as I mentioned here, theta is 90 degrees, so sin theta is 1. Okay, and dbx, this is db, and dbx is, there is a cos phi involved. Okay, db is this one. If you want, you can write the db over here. Okay, it is mu naught by 4 pi I dl sin 90 by r square. Okay, sin 90 is 1, so we have omitted it over here. Now let's try to simplify. So what we will be doing, first of all, we have to simplify the cos phi. What is cos phi? So if you see, this angle, as I mentioned, is cos phi. So cos phi will be r base divided by hypotenuse, right? So it will be 1 by 4 pi epsilon naught I dl by r square into capital R divided by small r. Okay, now if you see that total magnetic field along the x will be, total magnetic field on the x component, or x component of the magnetic field, that is the existing magnetic field, will be to close integral dvx. Close integral means, again, we are starting point and ending point are same, that's why close integral. This sign represents close integral. Okay, so we have to integrate it. Starting point and ending point is same, that's why close, no limit over here. Now as you can see, if you are integrating this quantity, I is constant for a given loop, r is constant, small r is also constant for this point, p is fixed, so small r is also constant. So only thing that is changing is dl. This dl, we are taking small component along the length, so dl is only variable, remaining things are constant. So we can write 1 by 4 pi epsilon naught I into r divided by r cube. So r square into r is r cube, I into r is now friend, and here we have close integral dl. Now what is close integral dl? Close integral dl means the circumference of this circle. Close integral dl is circumference of a circle. So what is circumference of a circle? 2 pi r. So we will use that in our next stage. So the total magnetic field on the x-axis is given by Bx equals to 1 by mu naught. One mistake I made, please pardon me. It is mu naught by 4 pi, not 1 by 4 pi epsilon naught. So it will be mu naught by 4 pi. Someone might be crying, sir, you made a mistake. Yes, I made a mistake, but I corrected it. If you don't do that, your marks will be deducted, right? So if you find this kind of mistakes, you please correct it in your exam as well. Okay, so mu naught by 4 pi IR by small r cube into dl is 2 pi r, right? So now this 2 pi and 4 pi will be cancelled, and we get mu naught by 2 I r square divided by, now r cube, time for us to put the value of r is square root of r square plus x square, and to the power of cube is there. So we can write this as Bx equals to mu naught by 2 I r square by r square plus x square to the power 3 by 2. Now if they ask you what is the magnetic field at the center, generally it does not come, but the central magnetic field is very important, which is given by x equals to 0. Simply if you put the x equals to 0 over here, you will get the magnetic field at the center, which is given by mu naught by 2 I by r. Okay, this is also another derivation and also another formula. If it is not asked, you don't need to do that. If it is asked only, then only do that. But remember, this formula is essential for KCET exam. Okay, KCET and all the other competitive exam, this is being generally asked, not that one. That one also can be asked, but this one is important for all competitive exams. Now next, find the force per unit length between two parallel current carrying wires. So here we have two wires carrying current. Suppose this one is carrying current I1, this one is carrying current I2, and the distance between them is D. Let us consider a arbitrary length of L, small l. Okay, force per unit length we are trying to find. If they ask you force also, then also you have to find force per unit length. Okay, so first of all, this is an arbitrary length to very long thin wire carrying current I. Now when a current carrying wire is there in a it will produce its own magnetic field. So what is the expression for magnetic field due to a straight current carrying wire? Magnetic field due to a straight current carrying wire is given by, first of all, we are trying to find magnetic field due to this wire at the location of the second wire. Okay, so B1 is given by mu naught by 2 pi I by R. Okay, magnetic field due to a straight wire is given by mu naught by 2 pi I by R. Okay, so here it is distance is small d, B1 is given by mu naught by 2 pi I1 by D. Now, so what is the force acting on this charge? Force acting on this current carrying wire, say F on 2 due to 1. Force on 2 due to wire 1 will be given by, what is the formula? BIL sin theta. Okay, sin theta is here is 0, theta is 90 degrees, the angle is 90 degrees here. Okay, so we can say that magnetic field and current are in perpendicular direction, so angle is 90 degrees. This is B1. Okay, magnetic field due to straight wire is, if you put your finger on this direction, this will give you the direction of magnetic field, which is into the page of the paper. So force on 2 due to 1 is B1 I2 into L, or if you put the value, you will get mu naught by 2 pi I1 I2 by D into L. Similarly, force on 1 due to 2, that is force on 1 due to 2, can be calculated using the same law, that is B2 I1 into L. That will also be same value. As you interchange the I1 and I2, nothing changes. So because interchangeability is there, the formula will be same. Okay, you don't need to do it again. So these two forces are basically same in magnitude but opposite in direction. So magnitude wise, we can say that magnitude wise this force is F12 equals to F21. Magnitude wise, because magnitude is same, we can say that. So what is F? F is given by mu naught by 2 pi I1 I2 by D into L. So now divide this, we will get the force per unit length. So force per unit length is given by small f equals to force per unit length, which is given by mu naught by 2 pi I1 I2 by D. Now one more question comes along with this. Define 1 ampere from this. So to define 1 ampere, what you have to do, you have to take I1 equals to I2 equals to 1 ampere, and then D equals to 1 meter. Then force per unit length will become 4 pi into 10 to the power of minus 7 divided by 2 pi. So it will be 2 into 10 to the power of minus 7 Newton per meter. So if how to define Newton 1 ampere, you have to write that when 1 ampere current passes through two parallel current carrying wire kept at a distance of 1 meter, they will experience a force per unit length of 2 into 10 to the power of minus 7 Newton. Okay, that is the definition of 1 ampere. the electrical definition of 1 ampere. 1 ampere generally 1 coulomb by 1 per 1 second, but this is another definition in terms of force. So we always try to relate everything with force, because force is very something that we know. So this is one way to define ampere. Remember this. After that, if you put I equal to Y1, then F will be coming out to be 2 into 10 to the power minus 7 Newton per meter, and then you write the statement. Okay. Now let's move on. Now we are not discussing any ray optics related derivations, because ray optics is not that important for your board exam as well as your pre-board exam. In case they give you any derivations from ray optics, ignore it for your final board exam, okay? Because final board exam ray optics will not come. Wave optics we have tactically omitted, because we think that if you practice all the derivations along with these ones, then you should definitely get a derivation common. 3 derivations you have to write, you will get all the 3 derivations common if you practice these derivations only, okay? That is sufficient. So that's why wave optics derivation I have excluded. Again, otherwise 3 derivations are there from wave optics. If you are interested, you can go and study from our wave optics Brahmastra series. There all the derivations are done. So what is a rectifier? Explain the working of a full wave rectifier using a neat circuit diagram. Draw its input-output waveforms. A rectifier is an electric device that converts alternating current AC into direct current DC. Now this is the full wave rectifier. Remember, full wave rectifier is most important. This is the most common question amongst all the other 2 derivations. Okay, 2 derivations, full wave and half wave. Okay. During the positive half cycle of the input AC, the upper half of the transformer secondary windings becomes positive. Diode D1 becomes forward biased and conducts, allowing the current to flow through the load in the direction. Okay, diode D2 is reverse biased and does not conduct. So when the positive half cycle means this is positive half cycle, okay, this is positive half cycle, so this diode conducts and current is passing through this. In the negative half cycle, that is this one, so negative half cycle with respect to this, okay, this becomes forward biased, and again the current is passing through the same direction. So in both positive and negative half cycle, because of the reference is taken from the center, okay, the diodes behave differently and they conduct differently. Okay, so during the negative half cycle of the AC input voltage, the lower half of the transformer secondary winding becomes positive, diode D2 becomes forward biased and conducts, while the diode D1 is reverse biased and does not conduct. Current again flows through the load resistor RL in the same direction during the positive half cycle. So this is very, very important to mention. Okay, current flowing in the same direction. Okay, so the output waveform is given by this. Next is, what is a half wave rectifier? Explain the working of a half wave rectifier using a neat circuit diagram. So half wave rectifier is a electronic circuit that converts alternating current AC into direct current DC by allowing the current to flow only during one half cycle of the AC input signal. The other half of the AC input signal is blocked, so only half of the AC waveform is used. Okay, and this is the circuit diagram. In half wave, only one diode is there, and don't miss the diagram difference between full wave and half wave. Okay, that is very, very important to remember. Now positive half cycle, the graph. During the positive half cycle of the AC input, the P side of the diode is positive with respect to the N side. The diode becomes forward biased and conducts current, flows through the load resistor RL in one direction, and the voltage across the load is positive. During the negative half cycle of the AC input, the P side of the diode becomes negative with respect to the N side. The diode is reversed bias and does not conduct. Current flows through the load resistor RL and the output voltage is 0 during the half cycle. Okay, so half cycle, positive and negative, full wave and half wave rectifier, both rectifiers are very, very important. One of the rectifier is going to come in your pre-board for sure. Now we are going into the numerical section. We will start solving numericals one by one. Now let us continue with the numericals. First numerical. Now here we will be discussing the numericals from alternating current and ray optics first. Then we will be solving some numericals from your electric charges and field and electrostatic potential chapters. We are not solving any current electricity numericals right now because obviously time is short. but definitely we will be covering all the numericals including current, electricity for your board exam. For pre-board exam, these are the few numericals we are solving, selective numericals, which are repeatedly coming in your board exams, in your pre-board exams. Exact questions may not be coming, but yes, the type questions will definitely come. Let's see. First question, a series LCR circuit connected to a variable frequency 240 volt. So remember that whenever a variable frequency 240 volt source, okay, variable frequency and 240 volt source. So frequency is variable, but source is 240 volt. Remember, if nothing is mentioned, it generally refers to RMS voltage. It generally refers to RMS voltage. L is given by 5 Henry. Capacitance is given by 80 microfarad. Resistance is given by 40 ohm. Determine the source frequency which drives the circuit in resonance. So first of all, you have to calculate the resonance frequency. Obtain the impedance of the circuit and the amplitude of the current at the resonance frequency. So here you have to calculate the amplitude of the current. Amplitude of the current means maximum current, which is slightly different than that of resonance value. Okay. Determine the RMS potential drops across the 3 elements of the circuit. So as I mentioned, if nothing is mentioned specifically, you can take this as RMS voltage. So from this voltage you can easily calculate the last part. For the second part, you have to do a little bit tricky, okay? But let us first start with the part A, that is calculating the resonance frequency. So what is the formula for resonance frequency? We know that resonance frequency is given by 1 by 2 pi square root of L into C. Now L is 5 Henry, C is 80 microfarad. So we will be calculating that 1 by 2 pi square root of 5 into 80 into 10 to the power of minus 6 microfarad, right? So now simplify that, we get 1 by 2 pi square root of 400 into 10 to the power of minus 6. Right, now 400 into 10 to the power of minus 6 is what? So that will be 4 into 10 to the power of minus 4, right? 400, 2 zeros are here, so you can take these 2 zeros and cancel with 10 to the power of minus 6. So it will be 1 by 2 pi square root of 4 into 10 to the power of minus 4. Okay, now if you take the square root, what we will get? You will get 1 by 2 pi into 2 into 10 to the power of minus 2. Okay, so now you have to simplify a little bit more. So what you got 2 into 2, that is 4 pi, and you got 10 to the power of minus 2 in the division. So 10 to the power of minus 2 in the division, this 10 to the power of minus 2 will go up and it will become 100. 10 to the power of minus 2 is in division, so it will go up and become 10 to the power square. 10 to the power square means what? 100 divided by 2 into 2, 4 into pi. Okay, so it will be 25 divided by pi. 25 divided by pi. Now you are allowed to use simple calculator in your board exam as well as pre-board exam. So you can simplify this, it will come out around 8. Okay, you can calculate the exact value, but here I do not have the access to calculator, so I can say that 3 8 is 24.14, so it will be close to 8 hertz. Okay, now let's move on to next part. Next part is where we are talking about obtain the impedance of the circuit and amplitude of the current at the resonance frequency. So at the resonance frequency, you have to remember that at resonance, this is resonance frequency. So at resonance, XL is equals to XC. Okay, this is part B. At resonance, XL is equals to XC. So what is impedance? Impedance is given by square root of R square plus XL minus XC whole square. So these two are equal, so that means XL minus XC will be 0. So impedance is simply R. Okay, so impedance of the circuit at resonance is equals to R. So we can say that what is R here? R is given by 40 ohm. So impedance will be 40 ohm. So impedance is calculated. Next, what you have to find the amplitude of the current. For calculating the amplitude, first of all you have to calculate the RMS current. RMS current is Vrms divided by Z. So Vrms is 240 given in the question. divided by 40 is the impedance we have calculated, 0 0 cancels, so we get 6 ampere. So 6 ampere is the RMS current. So what is the amplitude? Amplitude of the current I max is given by I RMS into root 2, that is 6 root 2 ampere. 6 root 2 ampere is the maximum value of the current or amplitude of the current. Clear? Next part, last part, part C. It says that determine the RMS potential drops across the 3 elements of the circuit. So how to find the RMS voltage drop? So VR, voltage across the resistance, is resistance times the RMS current. Now what is RMS current? RMS current we have already calculated, 6 ampere. So we just need to put that value over here. R is what? R is 40 and it is 6, so it will be 240 volt. So this is the RMS voltage. Okay, what about IVL? VL is given by XL into IRMS. Now what is XL? XL is given by 2 pi into F naught into L into IRMS. Why so? Because XL we know is 2 pi F into L. Okay, in this case it is F naught, so 2 pi F naught L into IRMS. Now let's put, now here what we will be using? We will be using, for value of F naught, we will be using 25 by pi. 25 by pi, so that pi gets cancelled. So that is one way to avoid calculator. So it will be 25 divided by pi into L is 5 and IRMS is 6. So pi cancels. What we got? We got 5 to the 10, 60, 6 into 25, 1200, 15. Okay, so it will be 1500 volt. Now at resonance, VL and VC are equal. So VC should also be 1500 volt because it is also equals to VL. Okay, at resonance, voltage drop across the capacitance and impedance are same. So this is the RMS voltages across resistances, across inductance and across capacitor. Slightly longer question, but longer questions are common in your pre-board exam. Okay. So now as I mentioned, it is not exactly 8 Hz, it is 7.96 Hz. 40 ohm is the impedance, we have already figured that out. Maximum current is 6 root 2 ampere and voltage across the resistance is 240 and voltages across the other two components are 1500 volt. Okay, clear? If you have any more doubts, please mention that in the comment. Now next, a series LCR circuit contains a pure inductor of inductances 5 Henry, a capacitor of capacitance 20 microfarad and a resistor of resistance 40 ohm. If the AC source of 200 volt 50 Hz present in the circuit, find the impedance, also find the resonant frequency of the circuit. So you don't need to find current, only resonant frequency and impedance. First of all, we will find the impedance. To find the impedance, we will use the given frequency which is 50 Hz. So how to do that? Obviously first step is to calculate XL. So XL is given by XL 2 pi F into L. Remember these two formulas are very important, XL and XC. So what is 2 pi? 2 into 3.14 into frequency is 50 and L is 5. Okay, 5 Henry. So what you will get? You will get this as 100 into 500 into 3.14. So 500 into 3.14 will be about 1570. Okay, it will be approximately 1570 ohm. Okay, you can use the calculator to calculate exactly. As I mentioned, I don't like to use. XC is given by 1 by 2 pi FC. Okay, the formula for XC is 1 by 2 pi FC. These two formulas you cannot forget. These are the very easy formulas to remember, and that is given by 1 by 2 pi 2 into 3.14 into frequency is 50, and the capacitance is given here as 20 microfarad. So 20 microfarad. Now micro means 10 to the power of minus 6. So what you have to do, you have to take this 10 to the power of 6 in the plus portion, and then you multiply other things. So what you got, 2 into 50, 100, 100 into 20 is 2000, 2000 into 3.14 will be, okay, let's solve this. Let's keep that 3.14 for 3 now, okay, so that we can cancel some of the values. It will be 6000 approximately. Obviously exact value is not that, so we can cancel 3 zeros with the 10 to the power of 6. So we got 10 to the power of 3 divided by 6, which is 1000 divided by 6, and if you can calculate, it will be around 150, approximately 150. I don't want to give you the exact value. Exact value you can calculate, that is not a trouble, because you have access to calculators. And in your PU board exam as well as in your pre-board exam, both type of exams, they give you the values where you have to use the calculator, okay. You cannot solve it without using calculator. So keep your small simple calculator handy. That is very, very essential to carry during your pre-board exams as well as in your final board exams. Now what is the impedance? Impedance is given by square root of R square plus XL minus XC whole square. So it will be square root of 40 square plus 1570 minus 150 whole square. I think if I remember it correctly, it will be 1412 ohm. Okay, so approximate value of the impedance will be 1412 ohm. Now this is not over, this is part A only. We also have to calculate the resonance frequency. How to calculate resonance frequency? Simple, same formula, 1 by 2 pi square root of LC. Okay, so it will be 1 by 2 pi square root of 5 into 20 into 10 to the power of minus 6. Don't forget this 10 to the power of minus 6 while calculating XC, as well as if you are solving resonance frequency. This 10 to the power of minus 6 in microfarad, most student misses, and they get 0 marks if they are not careful. So this is very, very essential to remember about microfarad. Micro means 10 to the power of minus 6. Don't make that mistake. Now let's simplify. So it will be 1 by 2 pi into 5 into 20 is 100, 100 into 10 to the power of minus 6 will be 10 to the power of minus 4. So it will be 10 square by 2 pi, so that will be 100 divided by 2 pi, so it will be 50 by pi. 50 by pi will be approximately 15 point something. I am saying 16 hertz. Okay, again 16 hertz. I don't want to approximate. So 1412 ohm is the impedance of the circuit, and approximately 16 hertz is the resonance frequency. Okay, easy question, not difficult, and this is much simpler and easier than the previous one, right? Now next, a sinusoidal voltage of RMS value 200 volt and frequency 50 hertz is applied to a series RC circuit in which R is 3 ohm, C is 800 microfarad. Calculate the impedance of the circuit, the current through the circuit, phase difference between the current and the voltage. So you have to do 3 things. First stage is to calculate impedance. Now in normally what we have XL minus XC, but here it is only an RC circuit, so L is not there, only R square plus XC square is sufficient. Okay, XL is missing, so you can simply use the value of XL to be 0 and you can calculate the impedance. So obviously first stage is to calculate XC. XC is 1 by 2 pi F into C. Now what is 2 pi into F is 50 hertz and C is 800 microfarad. So microfarad, I generally tend to write it like this. Microfarad, 10 to the power of 6 goes up. 10 to the power of minus 6 in the division, that can be written directly like this. This will save you some time only. Okay, so what we got? We got 10 to the power of 6 divided by 2 into 50 is 100. 100 into 8 is 800 is 8 into 10 to the power of 4 into pi. 2 into 50, 100, 100 into 800. Okay, so there are how many zeros are there? We have 4 zeros, so that's why we have written it like this. Why so? Because we can cancel it and we get this as 100 divided by 8 pi. Okay, so this is XC. So it will be 100 divided by approximately 25. Approximately 25, so approximately this will be 4 ohm. Okay, you can check that out. So it will be XC will be very close to 4 ohm. So what is impedance? So impedance is given by square root of R square plus XC square. So 3 square plus 4 square. So what is the value? 3 square plus 4 square? You should know that, right? So R is 3 square plus 4 square. So we get this as 25. That is 5 ohm. So impedance of the circuit is 5 ohm. This is part A. Next, the current through the circuit. Next step is to find the current through the circuit. How to find the current? Current is basically voltage divided by impedance. Voltage here is 200 and impedance we have calculated 5. So it will be 40 ampere. So current in this case is 40 ampere. What about the next? Find the phase difference between the current and the voltage. So phase difference is very simple. Tan inverse XL minus XC divided by R. So here XL is not there, so it will be XC by R. Remember, XL minus XC divided by R is in general, but because XL is not there, it will be only XC minus XC by R. Okay, so it will be tan inverse XC is 4, R is 3. So this value is very common with the angles. It is basically 53 degrees. 37 degrees and 53 degrees are important angles. You should remember them as well. Okay, 37 is 3 by 4, 53 is 4 by 3. Tan inverse. In case of sine also you can calculate. 37 is 3 by 5, 53 is 4 by 5. Cos also similar. Cos 37 is 4 by 5, cos 53 is 3 by 5. Okay, so these two angles are important angles. So this is your part B answer. This is your part C answer. Okay, so if you see the answer, it comes out to be 5 ohm, 40 ampere, 53 degrees, right? Next question, an object is placed at a distance 0.3 meter from a convex lens of total focal length of 0.2 meter. Find the position and nature of the image formed. Also find the distance through which the object should be moved to get an image of the linear magnification -1. Okay, we will solve it one by one. So first is, it's a convex lens, and in case of ray optics related questions, try to draw the diagram first. Okay, ray optics is one place generally questions can be easier, so that's why we are solving it. So an object is placed at a distance 0.3 meter, so distances are given in meters, from a convex lens of focal length 0.2 meter. So object distance is minus 0.3. Focal length is 0.2 meter. Convex lens have positive focal lengths, right? Convex means positive, concave means negative, always for mirrors or it is lenses. Okay, remember this, convex is positive, concave is negative for lens as well as mirrors. Find the position and nature of the image formed. So first stage is to find V. So we know that 1 by V minus 1 by U equals to 1 by F. Before inserting the value, try to simplify it first. 1 by F plus 1 by U, or V equals to UF by U plus F, right? you can write this is based on simple concept based on parallel combination of resistances or a series combination of capacitors, right? Similar to that. Okay, now we have to put the values here. U, remember U is minus 0.3 meters and focal length is plus 0.2 meters. So put these values in this equation. So minus 0.3 into 0.2 divided by minus 0.3 plus 0.2. Okay, so what we got? We get here minus 0.06 divided by minus 0.1. So it will be plus 0.6 meters. So the image is 0.6 meters, so it will be forming on the other side. Definitely forming on the other side means it's a real image. Okay, so nature of the image is real. So image distance is 0.6 meter and it is a real and inverted image. Okay, why real and inverted? Because we know that if convex lens image is forming on the other side of the lens means it's a real image, and real images are always inverted, so that's why it's a real and inverted image. Next part they have asked, also find the distance through which the object should be moved to get an image of linear magnification minus 1. So linear magnification is minus 1, is we get linear magnification equal to minus 1 when the object is placed at 2f, that is 2 into 0.2, that is 4.4 meter. Okay, so if you place the object at 0.4 meter, okay, then only you will get the real image, which is with magnification minus 1. So magnification minus 1 means the image will be exactly at the size of the object and the distance of the object should be equals to distance of the image. So in that case it is only possible when the object is placed at 2f. Remember, right, for concave mirrors it is exactly at the radius of curvature. For convex lenses it is exactly equals to 2f. So what should be the distance by which you should move? You should move the object by 0.4 minus 0.3, that is by 0.1 meter. So the object should be moved 0.1 meter away from the lens. Right, you can move the object towards the lens or away from the lens, both of it is possible. So mention that 0.1 meter away from the lens, then it will give you a clarity that where you are moving the object. Okay, so 0.6 meter and it is real, and you have to move it by 0.1 meter away from the lens. Next question, two lenses of focal length 0.2 meter and 0.3 meter are kept in contact. Find the focal length of the combination, calculate the powers of two lenses and combination. Okay, so when two lenses are kept in contact, their equivalent focal length is given by 1 by f1 plus 1 by f2. Okay, f is equivalent focal length, right? So now from here you can write f equals to f1 f2 by f1 plus f2. Okay, now two focal lengths are given, 0.2 meter and 0.3 meter. So let's put that 0.2 into 0.3 divided by 0.2 plus 0.3. So it will be 0.2 into 0.3 divided by 0.5. So 1 point you can cancel and you get this as 0.6 by 5. So it will be 0.12. Okay, so the combined focal length is 0.12 meter. What about the power? This is the part A of the answer. Now this is not over, you have to also calculate the powers of the two lenses and the combinations. So power is given by 1 by f when f is expressed in meters. Fortunately both powers are both focal lenses are given in meters, so you don't have to do too much work over here. Otherwise, if it is given in centimeter, remember that power is given by 100 by f in case a focal length is given in centimeters. Okay, this is a shortcut you should remember. Okay, if it is given in meters, you can directly divide. In case it is given in centimeter, to calculate power you have to do it 100 by focal length. Okay, this is the shortcut. Now here it is 1 by 0.2, so that will be 10 by 5, 10 by 2, that is 5 diopter, plus 5 diopter. Okay, plus 5 diopter. This is convex lenses. Okay, focal lengths are positive, that means power should also be positive. What about power 2? Power 2 will be 1 by 0.3, that is 10 by 3, that is 3 3 is a 9, 3.33 diopter. Remember, the unit of power is diopter. You have to mention the sign as well as the unit. What about the combined power? Combined power is given by P1 plus P2. Powers can be simply added, so it will be 5 plus 3.33, which will be 8.33. This is a question which repeatedly came in many pre-boards in the past. This is a question which repeatedly came in many pre-boards in the past. Answer is wrong. Ignore this answer. Something is not matching. Obviously 91 centimeter cannot be the answer. Okay, so 0.12 meter and 8.33 diopter are the answers. Next question. A prism of angle 60 degrees produces angle of minimum deviation 40 degrees. What is its refractive index? Calculate the angle of incidence. So first of all, a prism of angle 60 degree produces an angle of minimum deviation 40 degrees. So you have to calculate the refractive index. Refractive index is given by n equals to sine A plus delta m by 2 divided by sine A by 2. Okay, it's very simple. So A is 60 degrees, delta m is 40 degrees. So sine 60 plus 40 divided by 2 divided by sine 60 by 2, which will be sine 50 degrees divided by sine 30 degrees. Now here it can be little tricky. Okay, because sine 50 degree is not clearly known. So to find the value of sine 50, you can use the sine cosine table, which is very easy. 50 degrees value is easy to find, 51 or 53, and especially taking the inverse values are tricky. Sine 50 you can easily find from the sine cosine table. Okay, I will explain it in some other video how to find the values of sine cosine from the sine cosine table. But anyway, first sine 50, what I will be doing, I will be taking this approximately closer to sine 53. Sine 53 is something we can easily find. Sine 53 is 4 by 5. Okay, so that value we will be taking. Remember, your calculators are not scientific, so you cannot calculate sine 50 degrees using that calculator. Okay, if it is a scientific calculator you could have, but scientific calculators are not allowed. So 4 by 5 divided by sine 30 is half. So you get this as 8 by 5, which is approximately 1.6. Okay, I know this value will not exactly match, but it is very closer to our result. Okay, so this is sine 50 degrees. Refractive index is calculated. Now what about angle of incidence? Angle of incidence, so in this formula we are using lenses formula. Okay, lenses. So lens formula says that sine I by sine R. Refractive index is sine I by sine R. So basically this angle itself is sine is I. So I equals to nothing but A plus delta m by 2. So A is 60, delta m is 40 divided by 2, so it will be 50 degrees. Okay, so I equals to 50 degrees. Okay, so so if you put the exact values, angle of incidence is calculated wrong, it is be 50 degrees. Okay, so this is wrong. Angle of incidence is 50 degrees and the refractive index is 1.53. Next, 2-point charges of plus 2 nanocoulomb and plus 6 nanocoulomb are placed at the points A and B respectively, separated by a distance of 0.2 meter in air. Find the magnitude of the resultant electric field at the midpoint O of the line joining A and B. What will be the magnitude of the resultant electric field at O if plus 4 nanocoulomb is added to plus 2 nanocoulomb charge? So here we have two charges. Okay, one is at A, and at A we have plus 2 nanocoulomb, and at B we have plus 6 nanocoulomb. Okay, now separated by a distance of 0.2 meter. So the distance between them is 0.2 meter. So they asked at the center of these two line joining the charges, okay, the electric field at the midpoint. So what is the electric field at this midpoint? So first of all, if this is a midpoint, this will be 0.1, this will also be 0.1, half of this value, right? Midpoint means half of the total distance, so both of them will be 0.1 distance. Now what about the electric field due to A? Electric field due to A, both are positive charges, so electric field due to A will be in this direction, and electric field due to B will be in this direction. So if we can calculate these two electric fields separately and take the difference between them, we will find the net electric field. Why difference? Because they are acting in the opposite direction. Suppose one of them is positive, one of them is negative, then both of them will be in the same direction. So don't guess that all the charges will be positive always. One of them can be negative, one of them can be positive. So always remember, when calculating the electric field, this type of diagram is very, very essential. And so once you have drawn the diagram, make sure that you are also pointing the direction of the electric fields. It will help you to understand that what is EB, what is EA, and how to add them or subtract them. Okay, because if they are in the same direction, you add them. If they are in the opposite direction, you subtract them. Remember, positive charge electric field is always away from positive charge. Both of them are positive, so due to plus it is away from, due to plus it is away from. Okay, starting from your point, it should be always away from. If this is negative, this is positive. Negative means it will be towards, positive means it will be away from. So in that case, you have to add it. That's why I always recommend, do not use the sign of the charges, only find the direction of the electric fields, and then based on the final electric field direction, you have to add them or subtract them. Clear? So first let us find what is EA. We will calculate EA first. So EA is given by K into QA by R square. What is K? K is 9 into 10 to the power of 9. QA is 2 nanocoulomb. Nano means 10 to the power of minus 9. What about R? R is here, it is given directly in meters, so no need to convert into any units. Okay, so 10 to the power of 9, 10 to the power of minus 9 cancels, and we get 18 divided by 10 to the power of minus 2, that is 1800 Newton per Coulomb. You can check that out using a calculator. Okay, so it will be 0.1 in division, so it will be 10 to the power of minus 1 whole square, so that is 10 to the power of minus 2 in the division, and that's why it is 1800 Newton per Coulomb. What about EB? Now let's calculate EB. EB is given by same formula, K into QB divided by R square. Distance is same, that's why I am writing both of them as R. So K is obviously 9 into 10 to the power of 9. QB is 6 into 10 to the power of minus 9. divided by again 10 to the power of minus 2. Okay, 0.1 whole square is 10 to the power of minus 2. 10 to the power of 9, 10 to the power of minus 9 cancels, so it will be 5400. So it will be 5400 Newton per Coulomb. So what is the net electric field? Net electric field, as I mentioned, will be EB minus EA. Right? B is more, A is less, so that's why EB minus EA. So it will be 5400 minus 1800. So it will be I think 3600. 3600, 44, 56, 54. Okay, so 3600 Newton per Coulomb is the net electric field at the center. Now, if you add plus 4 nanocoulomb to 2 nanocoulomb, so what will be the net charge at EA? So part B at EB, new EB, sorry, not new EB, EA, new EA will be plus 2, already there, plus 4 you are adding, so the net charge will be plus 6 nanocoulomb. So in this case you have plus 6 nanocoulomb over here, plus 6 nanocoulomb over here, so the electric field at the center will be 0. Okay, so both will be equal and opposite, so they will cancel each other, so net electric field will be 0. So because EA dash is equals to EB, net electric field at the center will be 0. Okay, so correct answer is 3600 Newton per Coulomb for part A and 0 for part B. Let's move on. Next question. A conducting sphere of radius 10 centimeter has an unknown charge. If the electric field 20 centimeter away from the center of the sphere is 1.5 into 10 to the power of 3 Newton per Coulomb, points radially inward, what is the net charge on the sphere? So here we have a 10 centimeter radius sphere. Okay, so the radius of the sphere is 10 and we are trying to measure an electric field which is at a distance of 20 centimeter, and the electric field we have calculated is this. So from the application of Gauss's law, we know that electric field at a distance outside the sphere is given by K Q enclosed by R square, only when R is greater than the radius. Okay, so this is radius, this is small r. If R is greater than radius, this formula is valid. If R is less than small r, then electric field is 0. Electric field inside a spherical conductor or inside a charged conductor or charged shell, okay, electric field is always 0. Okay, now let's put the values. E is given by 1.5 into 10 to the power of 3. K is 9 into 10 to the power of 9. Q enclosed is trying to find, and R is 20 centimeter. So whenever centimeter is given, you have to multiply 10 to the power of minus 2 to convert into meter. Okay, so R is 20 centimeter. So that means that will be 20 into 10 to the power of minus 2 meters. Remember this conversion, it will make your life a lot easier. Now, so Q enclosed equals to 1.5 into 10 to the power of 3 into 400 into 10 to the power of minus 4. So this goes over here, cross multiplication comes over here, this will be in the division, divided by 9 into 10 to the power of 9. Now this one we have separated, so this one stays on our left hand side. Okay, now only simplification is what we needed. So we can say that this will be 1.5 into 4 is 6 into 10 to the power of 3, 4, 5 minus 1, so 10 to the power of 1 divided by 9 into 10 to the power of 9, or 60 divided by 9 into 10 to the power of 9, minus 9. Okay, this will go up. So 3 3s are 9, 3 20s are 60, so it will be 6.66 or 6.67 nano coulomb. Minus 9 means nano coulomb. Okay, so at this stage it was coulomb, and after this it will be 6.67 nano coulomb. Okay, and because the electric field is inward, so because the electric field is inward, the enclosed charge will be minus 6.67 nano coulomb. So sign of the charge will be negative, and do not miss on the negative sign, otherwise you will be losing marks. Now obviously magnitude is written over here, sign will also be considered because it's radially inward, means the charge is basically negative in nature. Now let's move on. Two charges of 10 microcoulomb and 5 microcoulomb are 12 centimeter apart. Find the work done in bringing the charges 2 centimeter closer. So here we have two charges. Now this is from the chapter electric potential and capacitance. One is 10 microcoulomb, another one is 5 microcoulomb, and the distance between them is 12 centimeter. Initially 12 centimeter. Now if you want to bring them closer, okay, you have to do some work done. Now how to solve this question? Okay, let me draw it little bit lower. So here we have two charges. The separation is 12 centimeter initially. Okay, one of them is 10, another one is 5. Both are microcoulombs. Okay, now if you want to bring them 2 centimeter closer, then what will be the new distance between them? The new distance between them will be 10 centimeter. Now it does not matter which charge you bring, okay, as long as the distance is maintained such that they are closer by 2 centimeter, that is what matters. Okay, you can bring both charges, you can bring only one charge, keeping another charge fixed, right? So the distance between them is 10 centimeter, so you have to calculate the work done. How to do that? You have to calculate the total energy of this system and total energy of this system. Then you have to find the change in potential energy by calculating final minus initial. So that much work you have to do. So what is the potential energy formula? Potential energy is given by K Q1 Q2 by R. K Q1 Q2 by R. So U1 will be K Q1 Q2 by R1. What is R1? This is R1. This is R1. And this is R2. Okay, now put the values. 9 into 10 to the power of 9 into Q1 is 10 microcoulomb. 10 into 10 to the power of minus 6. Micro means minus 6, right? We have solved so many questions in micro now. So put the values, and R1, here it is not square, it is R1 only, and distance is 12 centimeter. So as soon as you see a centimeter, you have to put a 10 to the power of minus 2 with it. Okay, now let's simplify. So you can simplify 45 by 12. Okay, 45, 5 9s are 45 divided by 12, rest will be balanced in the 10 to the power of values. 10 to the power of 9, here we have 10 to the power of 1, minus 6, and this will go up and it will become plus 2. Okay, so everything is accommodated in this value, right? So if you see 9 plus 1, 10, 10 plus 2 is 12, plus 12 minus 12, so 10 to the power of 0. What is the value of any number to the power 0? 1. So this entire thing is actually 1. So we get this as 45 by 12. Now we can even simplify this. 3 4s are 12, 3 15s are 45. So this will approximately 4, 3.9, but we will not simplify it yet. We will keep it as it is, 15 by 4, and unit will be potential energy, so it will be joules. Okay, so it will be in joules. Now what about the potential energy when they are 10 centimeters? So when they are at 10 centimeter, the new final potential energy U2, I need a slight more space, so let me erase this. Okay, the space is not enough. Okay, so now new potential U2 will be K Q1 Q2 by R2. Okay, so everything is same, only thing that changes is this R2. So we can say that U2 is equals to what? So the numerator will the top portion of the equation will be same, 9 into 10 to the power of 9 into 10 into 10 to the power of minus 6 into 5 into 10 to the power of minus 6 divided by 10 into 10 to the power of minus 2. Okay, so this 10 cancels and we get 5 nines are 45 into 10 to the power of 11 minus 1, 10 to the power of minus 1, that is 4.5 joules. Okay, so initially, so you have to calculate it, it will be so let's see, 3 4s are 12, 3.3 by 4, 3.3 by 4 means 3.75. So this will be 3.75 joules. So the change in potential energy that you need is delta U equals to U2 minus U1. So the work done that you need to do is 4.5 minus 3.75, that will be 0.75 joules. So you need at least this much work to separate them by 2 centimeter, to bring them closer by 2 centimeters. So these kind of questions are very common in your pre-board as well as final board exam. So do practice this kind of questions as well. Now last question of the day, two capacitors of capacitances 2 picofarad and 4 picofarad are connected in parallel across 100 volt supply. What is the total capacitance of the combination? Determine the charge on each capacitor. Two capacitors of 2 picofarad and 4 picofarad are connected in parallel. So 2 and 4 are connected in parallel. So one of them is 2, another one is 4, and they are connected across 100 volt supply. They are connected across 100 volt supplies. First step is to calculate the equivalent capacitance or total capacitance. So total capacitance in parallel combination is simply addition. Remember, for parallel combination of capacitor, capacitance added. For series combination of capacitor, it is actually added reciprocally. Okay, so remember that. Don't get confused with resistance and capacitance. Okay, for parallel combination of resistance is slightly different, right? So 2 plus 4, that is 6 picofarad is the equivalent resistance, equivalent capacitance. I am also getting confused. So connected across a 100 volt supply. The supply is 100 volt. Now what is the total capacitance? Obviously calculated. Determine the charge on each capacitor. To find the charge, they will have different charges. Okay, so total capacitance is calculated. Now how to calculate the charges? Remember, in parallel combination, the potential drop across individual capacitors should be constant, and that is equals to this 100 volt. Okay, so 100 volt across 2, 100 volt across 4 as well. So for this one, we can say that Q1 equals to C1V. Okay, what is C? C1 is 2 picofarad. Picofarad means 10 to the power of minus 12. Pico means 10 to the power of minus 12 and times 100. So it will be 2 into 10 to the power of minus 10 Coulomb. Okay, and Q2 is given by C2V, that will be 4 into 10 to the power of minus 10 Coulomb. unit is very important. Okay, unit is very important whenever you are solving questions. Remember, unit and conversion of the values are very important. So for a first answer is 6 picofarad, second 0.2 nanocoulomb, 0.4 nanocoulomb, or you can leave it like this also, this is fine. Okay, so this is the end of this lecture. Thank you for being patient and watch this lecture till the end. Okay, and obviously after entire almost 4 hours lecture, I should always thank you, and I wish you all the best for your upcoming pre-board exam. Definitely you will do wonderfully well in your pre-board exam if you have prepared all the questions that I have discussed. And don't forget to like this video, subscribe to our channel if you have not done so yet, and I will be back with more content for your pre-board as well as your PU2 preparation. So don't forget to click on the bell icon so that you get the notification whenever we are doing something new. I'll be back. Till then, bye.